All right. Thanks, everyone. It's great to meet you all and to be here. And with that, I think we're ready to bring up our first speaker. Please welcome Bruce.
All right. Okay. Well, first off, this is the book I'm working on. It is available right now. It is in early form. A lot of it's been generated. I'm using all the tools I can get my hands on, but the examples all work. I have a build system that checks them all. Also, I have these stickers that look like this. If you're interested, I've got a box of them. And I'm building it in the open, so if anyone wants to make pull requests or tell me where I've made a mistake or where I've missed something, feel free to do so. There are several ways to do that. Also, there's a podcast that we've been doing for a few years, and we mostly interview people. We want to interview somebody from Astral, so maybe we can figure out who that is. Right. So a number of years ago, I found some research on how people were using generics in Java, the generic types in Java. And it turned out that the vast majority of people were using lists or maps, and they were actually using lists of strings and maps of string to string. So it's kind of embarrassing, I feel like, to say it in this group, but a string gives you virtually zero information. You have to take the string and figure out what it means. And we spend a ridiculous amount of our time doing this kind of thing. Phone numbers, for example, you would think would be types, but I have a friend who works at a company that deals with phone numbers, and he had to go in and tell them, show them how they could build a type that would solve a huge number of their problems. And they were very happy with that, but they hadn't figured it out themselves, even though the phone number was kind of the basic thing that they worked with. So what we usually end up doing is something like this. For every function that we have have to validate the argument. The argument is usually something, a name is different, but they're often strings, and we have to go in and figure out how do we want to validate the strings, how do we want to report the error. And each function can report the error however it wants to. So the first one prints an error message and returns. The second one does an assertion. The third one returns a string indicating it's. So it's all out there. If you need to change how you validate your phone number, you need to go through all of these different functions and make sure you get it right and align them and hope that you've caught everything and there's not something hiding that's going to cause problems later. So this fellow Bertrand Meyer, way back, he created a language called Eiffel, and he's a French guy. And in that, he came up with this idea of design by contract. So the idea was that there were certain things that you wanted to validate with every function that you created. And one of the things was a precondition. So we could simulate that by creating a tool which defines a condition and will implement that condition in different ways. And each condition has a check, which is a function that takes any number of arguments and returns a bool, and then a message which is produced if that function fails. And then we can create a decorator that decorates whatever function we want to check for, tests one or more conditions, and applies those, and checks each one and issues a failure. So, well, we could do that. And for example, a simple example of using this would be checking for, we want to take a square root, so the thing has got to be positive, so we can create a positivity condition. And our function checks to make sure it's positive, and our message gives us something reasonable about that. So if we do a square root of 4, that works fine. This double hash is I've got an automated system to output and embed code in examples for the book. So that's what the double hash is. And then the catch is for things that are going to throw an error, so it catches those and inserts the results in the book, so it makes it more readable. So we can see, that works pretty well. We could do this for something like a bank account. And so for bank accounts, we might want to check for a positive amount and a sufficient balance, and we simply create the condition objects for those, and then we can build our bank account. We're going to use decimals, of course, and so the deposit, we can say a deposit has to be a positive amount. One thing I didn't mention is in this case, you'll see, since we're applying these to methods, we need to have self as an argument in our lambda. And so I'll say, well, a deposit has to be a positive amount, and then a withdrawal has to be both a positive amount and there has to be a sufficient balance in the account. And well, this works okay. You know, we can create a bank account with a certain amount in it and deposit and withdraw. And if we withdraw too much, we get error messages. So it's okay, but it requires the programmer to acknowledge that these decorators exist and to apply them and to kind of know about them. And we can do better is basically what I'm saying. So here is, instead, let's start by creating an amount, which is a frozen data class. So we'll make everything immutable. That's always the safest thing to do. And the amount contains a decimal, but we will put constraints on it. So to create an amount, we'll be able to accept an int or a float or a string or something that's actually decimal. So we'll accept all those things. We'll check on a float. If it is a float, we'll do a couple of things. One thing is, if it's got an E in it, well, it's probably out of range. We'll just make that rule. If it's got an E in it, it's too big or too small, so we won't allow that. And the other thing we don't want to allow is decimal places greater than 2, because then we're dealing with weird round-off errors. And so we won't allow that data in. So you can't create an amount object that goes out of those ranges. And so we will create an amount, but we're not done yet because we're dealing with a data class, so we have the post init to make sure that it's not negative. If we, for example, if we were to insert a decimal value directly, it's not negative, and we don't have more than 2 decimal places here. And then when I define my adds and subtracts and everything else, because we're dealing with immutable objects, I can simply create a new amount from the existing amounts, and I never touch them, and they can't be modified. All right, and I can take that and I can compose with it. Oh, first we should see how it works. And so I can create an int or a string or a float, a decimal, and then if I try and do it incorrectly, once again it checks it. The key is, though, all the logic is in the construction of this object. And once it's constructed, it's frozen, so it can't be modified. And so once you're passing around these amount objects, you know you're safe. And if you ever have to change it, you do it only in one place, in the construction part of the object. So we can take this, and now we can compose with it rather easily. So if I want to create a balance for a bank account, I can simply use an amount and then add the deposits and the withdraws, and all it does is manipulate the amounts. We know that the amounts are safe, so we don't have to think about checking them at this point. If we ever make any changes to the amount, that will automatically basically flow through to my balance. then I can create a bank account by saying a bank account has a balance. Might have some other things too, but it has a balance. I can deposit just using the operations that I have already defined for my balance object, and withdraw, etc. And we can put all these things together and see how it works and catches any problems. And then if we go back and apply this to the phone number, the same approach to our phone number, we have a frozen data class. This is what we want to get, and our class method that is used to create phone number objects simply does some parsing, does whatever rule checking it can, and then the post-init catches everything else to make sure that it's all validated. And you could do all kinds of other validation if you wanted. And again, if you ever say, oh, we want to apply further constraints to our phone number, you do it in this one place. And then your frozen phone number objects are simply passed around. And the user of this class they don't have to think about it, which is, I think, super nice. And then we can create other operations, and the safety of that initialization is carried with us the whole time. And you could also imagine, say, this company that I mentioned that's doing phone numbers. Suppose it creates this phone number object, and they decide, oh, this is not efficient enough. It's not moving fast enough. Well, you could rewrite the phone number class in Rust and then import it, and then all of a sudden you've got all that speed up. And it's, again, all in that one spot. So this is sort of the idea of the single point of truth, and also don't repeat yourself packaged in one place. So if we apply the phone numbers here to our original list of phone numbers, you can see that it parses them all, and if there's anything invalid, it produces it. So once that phone number is validated, that object can then be passed around the rest of the system, and the consumers of that, all the functions that consume it, they never have to do any sort of validation. So that is what I was going to talk about. Please feel free to read, contribute, whatever to the book, and got a bunch of stickers there if you want them. And got questions? Yes?
Sure, yeah. Let's use the mic for questions.
Oh, okay.
Make sure the audience.
Yeah, thank you. Really interesting. I think it was a really instructive example of how to build up types. I'm curious about your opinion on protocols and how they influence this sort of style of object-oriented programming when it applies to types, for example, using data classes and making things, reducing runtime errors and such.
Okay. Are you asking, do I have an opinion on protocols, or?
No, just like whether this could be, like this example could be applied to protocols and.
Yeah. I think any kind of well, yeah, I mean, there's a chapter in the book on what is it called? It's a kind of typing, structured typing. Thank you, which is what TypeScript uses because of JavaScript and everything. And I think it's appropriate in places. It depends on the problem that you're trying to solve. Trying to make things as general as possible. I generally like the most abstract thing that I can get, and a protocol is typically more abstract than a concrete type. But I might, focus on the functions themselves, accepting protocols that a type might fit. I'd say it depends on what you're trying to do. I think one of the problems that we've had in the past, especially with object-oriented programming, is trying to get too general too early. Rather than saying, I think the tools that we have now allow us to start by solving the problem that we have, and then go back and say, oh, we do actually need this to be more general, so then we can add abstraction. Whereas what we've seen in Java is people deciding, they're saying, well, everything has to be some kind of an abstract base class from the beginning, and you get very confusing code because you don't know why they're doing it.
Thank you.
Sure. Okay. Oh, I thought you were going someplace with that. All right. Okay, everything clear to everybody, or is there anything? Okay. All righty then, thank you.
To accept something. Oh, no.
Okay. Okay, hello everybody. I'm Jukka, and I'm going to talk about using types to improve for efficient runtime object representations in mypyc, which is a compiler I'm working on. So mypyc is a Python to C compiler. More specifically, it compiles to C Python, C extensions. It was originally built to compile mypy to make it faster, because originally mypy was written in just regular interpreted Python, and it's not the kind of the best fit for writing an efficient type checker. So we got a lot of help from mypyc. So in very abstract terms, the way mypyc works, it takes like Python files. Then internally, it invokes mypy to type check the code and generate an AST, which is like a representation of the code as a tree, and with also inferred types for everything. So every expression and every function has a static type, and it falls back to any if there's no like explicit type. And then it does a bunch of magic. Inside, it kind of transforms the AST into an intermediate representation, and does some optimizations, transforms a bunch of stuff. And eventually, it ends up as C code, which is very like machine-generated looking, because that's basically what it is. And then we run a C compiler, and it produces a C Python C extension, and that can be imported then in any Python code. And ultimately, pretty much the only goal is to get as fast as possible. And in many cases, performance can be like 2x to 10x compared to regular Python, compared to like Python 3.13. But sometimes there's no improvement. So basically, it really depends on your workload. And here's just a very simple example of how you might use mypyc. So we have some program. It does some stuff, but it's kind of pretty slow. And then we pip install mypy. So mypyc is bundled with mypy. And then you run mypyc on the code, and then it generates a C extension, which might have like, on my system, it's like it has a SO file extension, and then you run it by importing it, because you can't run a C extension directly using Python. And then hopefully, if everything goes as smoothly, then it's much faster. Well, usually you also have to optimize the code a bit, so or maybe tweak it a little. But this is sort of the basic workflow. mypyc actually isn't really a Python compiler. It compiles language that kind of looks like Python, but it's kind of subtly different in various ways. So it's like it's a Python variant or subset. It's effectively a subset. You can think of it as, even though it's technically quite not. It's backward compatible with Python. That's kind of core constraint in everything that we do. So it needs to only use Python syntax, so that you can use like all Python tooling, like VS Code, PyCharm, whatever, it should work. And also like use a Python type syntax, or something that can be kind of can be mapped to like regular Python typing. And the compiled code also needs to run as regular Python. So the semantics need to be close enough that, okay, there are some edge cases where it might be different, but in general, in practice, you can always like just run your code using Python during development, and then you like compile it when you want to run it faster, when you like ship your like package on PyPI or something. And there are some semantic differences that are pretty important. The first is early binding, so which means like when you like calling a function, it tries to kind of decide which function is actually being called in compilation, so which limits monkey patching, but it kind of makes it easy to generate like efficient code and do like inlining and all sorts of stuff. And in this talk, the focus, I'm not going to talk about this. I'm going to talk about runtime representations, which kind of depends on enforcing static type annotations at runtime. So this kind of enables a bunch of stuff, nice stuff that we can do. This is a really tiny example. This is a function which like, doubles an integer. And then there's another function which doesn't have like strict types, which calls it. And then we call it with a string. So I know it's kind of obvious that there's like something kind of wonky going on. That's probably not a good idea. But if you run it as a normal Python program, then the types don't really mean anything at runtime by default. So unless you use like some library or third-party thing that actually introspects the types. And this kind of works, and you get like XX. But then when you compile the code and run it using mypyc, then actually the mypyc inserts like runtime type checks anywhere where things might be unsafe in terms of types. And then you get a runtime type error, so exception gets raised when you're trying to call D. So that's sort of, and this happens everywhere, so it kind of enforces that if something isn't declared as an int, then it will be an int. And now I'm going to talk about how CPython represents objects, because that's kind of the starting point. That's kind of the default. So mypyc can always fall back to this object representation. And we can make things still faster, but even though it kind of obviously limits us in certain ways. So on the left, there's some arbitrary Python object. It has a reference count, which used to like release the memory when the object is no longer used. And there's a type pointer. It's pointer to a type object, which kind of describes the object. And then there's a per instance data, which depends on the type of the object. So like things like attribute values, and basically. And then these like kind of thin arrows are like C pointer references. So there's another object, which like type is just another object. So from the representation point of view, it's just normal. And there's like another type of type, and etc. This is kind of a bit simplified. So depending on like if you use free threading and there's a cyclic GC and stuff like that, kind of makes things a little more complicated. But this is kind of, I think, right level of detail for this talk. And the other bits don't really ultimately change the picture significantly. Okay, here's a more concrete example. So this is, we create a float. This is kind of a silly example, but it's the idea that we attempt to construct a new float object. Like, I assume that that's actually what happens at runtime, which might not be the case. And so then we assign it to A. So I'm not going to talk about how the variable A is kind of represented internally. But anyway, the A contains a pointer to this float object. And it has a reference count. If you assume this kind of creates a new object, then it has a reference count 1, and then there's a pointer to the float type, and there's a value of the float. 2.8 is in the kind of instance per instance data. Okay, that's pretty straightforward. But then when you have a list, things are a little more interesting. Okay, like you still have the list object. It has a reference count. 1 is a like list type object, and then it has a length, and then there's a pointer to another heap allocated object which has the items, and there's like a length of that bit. They are not always like same. And then we have further pointers to all the like float objects within the list. So I guess you see like it's like a lot of pointers, a lot of kind of objects all around. That's kind of how Python works, and that's really good in the sense that because then everything is very uniform, everything is an object. So it's the programming model is really nice, but it's obviously kind of not necessarily the most efficient way to do things. So there are definitely some performance issues with this, especially if you're trying to get kind of potentially closer to like, C or C++ level performance, at least in certain cases, because everything is heap allocated. So this is kind of inefficient in terms of memory use, especially when you have like tiny objects like integers, floats, and stuff. So there's a lot of overhead. So it kind of like multiplies the memory use in some cases. Obviously, it's like NumPy and etc. But sometimes you just need list. And then these objects are allocated dynamically, which is generally kind of slow. There's like a cyclic GC involved and stuff like that. So this adds a bit of overhead. And also, when you're allocating these objects dynamically, they could be spread out across the memory. So you might have poor cache locality, which then again like impacts performance. And then we need reference counting to keep track of objects which need to be freed. And that means like when each time you like take a reference, like you might have to increase the read the old reference count and kind of then update it and write it back. And that's kind of memory operations are kind of somewhat slow, even if the data is cached. So that's latency. And then you can easily have like dozens of memory operations per like a trivial looking operation in Python if you use like interpreter. Obviously like 3.13 improves things. Things can improve, but still fundamentally like the overhead is kind of pretty big compared to like say Java or C++. Okay, so now let's see, can we use types? Obviously we can to for more efficient memory representations of objects. Okay, this is a trivial example. So you have bool type, then you have two values, true and false. So mypyc uses 1 byte for the representation. And it might effectively take more if depending on like alignment, there may be padding. But in the ideal case, it's only 1 byte. With Python, everything is referenced to an object, so it's like 8 bytes. So this, again, like nice improvement. What about integers? Another kind of like low-level sort of basic data type. In Python, again, it's a reference pointer, and then they have object, which is on the order of like 32 bytes for the typical sized integer. Whereas mypyc uses tagged integer representation, where if your integer fits within 63 bits, then you just need the 64 bits and like 0 bit to represent that. And if it's longer than that, because Python integers are arbitrary precisions, so we need to handle bigger integers. Then there's still a pointer, and then there's the object, and similar to the Python representation. But that's like most of the time not needed. So it's pretty rare to have like really big integers. And also, Python actually, for very small integers, it shares the representation. You have like one object for like 0 that's used in many places. So even Python is kind of, sometimes it can get kind of pretty close to mypyc, but it only depends on the values of your ints. MyPyc has also these fixed width integer types. So for example, I64 is just a 65-bit integer, similar to like you're doing like C pretty much. It's only 8 bytes ever. And again, like I32 is like 4-byte integer, until like I16 and etc. So this way you can just use as much memory as you need. And then let's go to a more interesting, slightly more complex example. Tuple of two 32-bit integers. So mypyc can represent that in 8 bytes. So just similar to what you'd need in C, because tuple is immutable, so we can just treat it as like a value that gets kind of copied around instead of passed by reference. With Python, you have the pointer as always, and then you have the tuple object, which is like on the order of like 56 bytes of memory, and then you still have the two integer objects in addition. So these could be on the, around like 128 bytes to represent, depending on the value of the, like the magnitude of the integers. So again, like this is like, yeah, these low-level representations can be kind of give you pretty big gains. Okay, but this, in the previous slides, I showed you there were like the I32 and I64 types, which were like new, they're kind of mypyc specific. They still kind of fall back to, so if you're using another type checker, they fall back to int. So basically, they kind of, there's like this kind of backward compatibility angle, but they are like new types. And they behave differently from the regular int in certain ways. I'm not going to go into details too much. And more generally, we'd like to do the same thing that we did like boolean, int, and tuple for like other common Python like types like list and dict and whatnot. But these are actually not that easy. These are mutable. They kind of have to be heap allocated because otherwise you turn it into values, then you kind of break semantics and kind of nothing is kind of backward compatible with Python. And even int and float that I showed you, they're not like 100% compatible with CPython. In Python, you can do a subclass of float. And if we represent it as a 64-bit float, then you kind of can't do that easily. So we kind of then fudge things a little bit. Normally it doesn't make a difference, but you can come up with examples where that's important. But for lists, like if you do lists into like a value object, something like that, it would kind of completely break everything. So like mental model and everything. So we can't do that. So the answer is creating new types. So something that you replace your list with when you kind of performance critical and you want. Oh wow, what happened? Yep, and the following types, there are like prototype implementations available, but they're still in work in progress. You can still play around with them. So the next concept is value types. So this is similar to the tuple example. So we have like object with two attributes. Let's say these are floats. And again, like Python, you have the pointer, and then you have the instance heap allocated. It's on the order of like 48 bytes. And then you have the two float objects. So that's obviously like not very efficient. But if you have a value type, then mypyc can represent in 16 bytes. So just like so it's basically the C struct with the two float or double fields. And we can represent that using a struct base class, a magic base class that does a bunch of stuff that I'm going to talk about in more detail. And these will be like a data class transform, or like PEP 681, which means that you can like you get like dunder in it and whatnot, all the kind of nice handy stuff for you. And again, like this can be made pretty much backward compatible, so this doesn't require like new type system concepts. But mypyc needs to kind of deal with this magic base class differently. And so how does it actually work? So like this is a value type, not a reference type. So you can have the value in line in the C stack in the generated code instead of always having a pointer to some like heap allocated thing. And also going to be stored in line in instances, like function arguments and so on. So that's kind of like a big thing for, especially small things, where so you don't need the per object overhead. But it also means like you can't do subclassing. Okay, plausibly you could do, but anyway, the implementation that we have in mind doesn't support, so everything is kind of final. The object needs to be immutable, because if assignment copies the value. So to make that behave the same as if it was like a reference, if it's immutable, it's kind of it behaves the same externally. So all attributes are final, so it's frozen implicitly. And yep, that's pretty much what's needed. So it still kind of falls back to more normal Python. We can support this thing. It just creates a normal frozen Python class. So all the kind of the hard constraints can be supported. Value types can be really good, but there are some like obvious trade-offs. So it's big reduction in memory use, especially if you have small objects like we have like two floats, and especially if you can, the item types can also have like efficient representations. And this means like fewer pointers, less pointer data referencing, because again, like it's kind of at some latency, generated code, fewer reference count updates, possibly. There could be also more, but as it is usually like kind of trivial data like ints and stuff, then it'll help with that. But then, what if you have a value type and you want to append to a list? List only supports normal Python objects. So then we have to box it. So basically allocate a normal class instance and copy the state to that, and then put it in the list. And when you read it from the list, if you do the other one, we like copy the contents of the object and put it in like a C local variable or like struct So that can actually make things slower. If you just put them always in a dict or list, then you might actually, the unboxing and boxing might kind of kill all your benefits. And also then, when it's boxed, it uses the same amount of memory as in Python, or like normal Python class. And also, if you're copying these a lot, then if you have many attributes, then it's obviously expensive, and if they're like reference count types, that's kind of even worse still. Okay, and I mentioned that lists are kind of hard to support, and the thing is, like CPU-intensive code tends to use a lot of like sequence types. So that's where you have like NumPy and other libraries that are kind of focused on like making array like types super efficient in Python, but these are not practical for like generic use cases like numeric types, because they're kind of like a lot of per instance overhead, and you have to like import NumPy, which is a big library, etc. So we kind of need something lightweight but efficient. And okay, this is the like my array type, which is not the final, and this is work in progress, but it illustrates the concept. So when you construct an instance of this, you always have to provide the type, because it will actually decide the representation of the array based on the item type. So in this case, it's a float array. So the idea is we can just have inline kind of float values in the array representation. And that's kind of one of the things that we get, which is not possible with list. The other one is we can make it a value object. So have it actually like two fields, like length, and then you have pointer to the actual data. So the value object is immutable, but the buffer is mutable, which means that we can get rid of one extra heap allocated object per like array compared to a list, which is actually a huge win, because this often is like loops and kind of super performance sensitive code. So basically we can like save often like 2 or more memory accesses when accessing like an item compared to like a regular list. And if it's like a float, then it might even more, because then you don't need to access another pointer to access the float data. So these could be a big win, and at least in like simple benchmarks, it's kind of, yeah, it's amazing, especially when you're using like int or float values. You can still append to these things, because it's like the buffer can have like extra gap, like empty gap. This is kind of similar how like Go kind of slices work. Not exactly, but kind of the same idea. Okay, this is pretty much what I wanted to say. So in summary, so static types, when enforced at runtime, and for this you need kind of a complete new implementation, or you can't just backport it this easily into CPython. So they enable efficient runtime object representations, as we've seen. And this object representation is actually key to many kind of fixing many performance bottlenecks and improving performance significantly. Because it can reduce the number of dynamic memory allocations, which are kind of expensive. It can reduce the number of pointer dereferences. In normal CPython, you often have like a pointer and pointer and pointer. You have to access like multiple levels of direction, and then each kind of adds some latency at the like CPU level. And then you can reduce the number of reference count updates, which were kind of expensive. In a 3-threading world, this might even be possibly more useful, but I haven't really thought about that too much. And then this can improve memory efficiency and locality, because options don't get like, they will not get as much spread out across the memory. So hopefully we have time for discussion. I kind of slowed myself down a little bit, because I figure we have some extra time. And we have some documentation. It's all, the code itself is in the mypy repo, and there's docs, read to docs, kind of.
That's a great talk. Thank you. Very cool. I have a couple questions. So one question, Python 3.14 is like 40 to 50% faster than Python 3.10, mostly due to the faster CPython teams work on doing things in the Python interpreter to improve the memory layout of objects in a lot of cases, and to dynamically do some of the specializing optimizations that mypyc is doing statically. So I'm curious how you've seen the performance wins that mypyc provides relative to the interpreter change over the last few years.
That's a very good question. So yeah, when we started working on mypyc, that was anyway, it was before all this faster CPython work. So we're kind of tracking the performance over time. So definitely in some benchmarks that we're looking at, like CPython is getting like twice as fast compared to like, I think 3.8. And so there's definitely, so the performance gap has narrowed on the other hand. On the other, we might be improving mypyc. So originally our goal when building mypyc was to make mypy like 3x faster. So we achieved roughly like 4x, but that includes some like tuning mypy, manually optimizing mypy code and stuff. And these days it's maybe like 3x or 3.5x. I haven't checked it with the latest like 3.14 betas. So we've kind of like been kind of keeping up pretty well. But there are some things like the immortal objects were introduced in 3.12. And that changed how reference counting works. So because reference counting is a super hot operation. It's like, this is like millions and millions of times each second if you're doing a CPU intensive code. And when you're compiling stuff, we actually still have to do pretty much like similar number of reference count operations, unless we can use these representations, which means that reference count operations will take like a larger fraction of your time. So when they added like one extra check to every reference counting operator, that actually cost us like 20% of performance in many cases. We clawed back some of that, but it's, yeah, so on the other hand, like, yeah, CPython has been getting faster and CAPI in some cases has been getting slower because then it kind of, the object representation is more complex and the CAPI can't take advantage of these optimizations, so it's just like new extra logic that kind of slows things down. So we kind of need to work harder, but there's like, as I said, like there's like more things we can do, like the value types and kind of replacement for list objects in certain cases. So I'm hoping that we can still stay kind of competitive.
It's impressive that you've kept up that well. My second question, so say I have a function that's annotated to take a list of integers, and I pass it under mypyc, I pass it a list of 1 million integers followed by a string. Mm-hmm. I'm curious what will happen at runtime under mypyc.
MyPyc will generate a type check on each time you read an item from the list. So we can't just check all the context because you might have like a 1,000,000-line list and then you only read one item in the function. And also like any kind of call to other code might modify the list. So basically, that's pretty much the only thing we can do.
So if the receiving function only reads the first item of that list, there will never even be a runtime error under mypyc? Okay.
That's correct.
Cool. Thank you.
Yeah, this is kind of a two-part question. So first, like, how do you do your calling convention? Like, if you call a function, do you still construct the Python object to hold the arguments and then pass that to the function?
No. So this is part of what I didn't focus on in this talk. So it's early binding. So again, it depends. But in general, if you call another function defined in the same kind of what you call like compilation kind of unit, usually mypyc can decide, like, oh, this is function f defined in module whatever, and then it directly calls that C function. It doesn't go through any like namespace dictionary or anything. And it's just, it translates, because then it knows exactly which function is being called. So it can translate like keyword arguments into positional arguments and etc. So it just gets translated in the typical case into just a regular C call with like positional arguments only. Okay. Obviously, if you do like star arcs and stuff like that, it gets kind of more complicated. But that's kind of, you shouldn't do that if you want like, if you're writing a like performance kind of critical code. Yeah. At least not too much.
So yeah, the second thing I wanted to follow on from that is if you store a function as a callback, do you need to do anything special or is it just a C function pointer?
No, if you each function also gets a Python function object. So there's a C function and then there's a wrapper function object. So when you use a function as a value, then we just refer to that Python function object, which is always available.
Thank you for the talk. I was wondering, when you were developing the data class sort of representation for mypyc, if you ever evaluated still using py objects, but maybe flattening the attributes into like a struct instead of having py object and like a dict for the data classes, and if that could like have some intermediate performance gain.
Sorry, can you talk about the value objects?
Yeah, so
or
for the struct class that you
Struct.
had.
Oh yeah, that one.
Yep.
So the key is that if we just have a regular class, we can still have the attributes directly within the py object struct. So we can have the header, and then we have the two float objects. So what the struct representation gives us, and again, this is kind of not properly implemented. Yeah, there's a kind of prototype which kind of isn't quite right, and it's not even written by me. But what it gives you that you don't need the object header or the pointer to the object. So
Right. But it would perhaps give you back the ability to pass it into a list without having to destructure it back into a py object or something like that.
yeah, you can do that already. You can just do a regular class. I think it does what you want. Just leave out the struct.
Okay.
That's only possible, but then it's not like the representation is kind of pretty close to what CPython uses. But yeah, but basically, all attributes by default get translated into like struct fields in the representation.
And I just wanted to tag one thing along with that is, how often do you find yourself actually using fixed size arrays across the code base?
Fixed size arrays. We don't have them in at the like a Python level. So we only have the new array type mentioned. It's actually not a fixed size array. So we have like capacity, and then we have the length. So when there will be there's an append function that returns, because it's an immutable object, so you can't have it like mutating. We can mutate the length using a method. So you have to like append function which returns either a reference to the same buffer with an incremented length. So we can return a copy of the value object with an incremented length, or if we reach the capacity, then it kind of say allocates a new buffer with double the length, and then it returns that instead.
Cool.
Does that make sense?
Yeah, thank you.
Yeah, thanks for the talk. And I was evaluating mypyc because I was writing like a compiler in Python. I needed to distribute it, like in the enterprise setting. We wanted to close the code basically. Mm-hmm. And I was looking at mypyc 2.5 years ago, and we eventually went with Nuitka. What I was curious, there's Python, there's a whole ecosystem of making Python quicker. There's modular language. They're trying to do the superset for data scientists, and then there are compilers, and there's also PyInstaller, which is just wrapping Python code. So what? And I see that you're still developing it, right? And you're trying to go beyond just application for the MyPy itself. So what do you say would be the best, where mypyc would be a first choice, like among all of this kind of options, right?
Yeah, so we definitely want to build mypyc into a general purpose, like useful thing. It's still marked as experimental. We're kind of actively working on making it kind of stable first, and then fixing like the biggest bottlenecks, like similar to what I've shown you, a few others. And then I'm hoping that it can be pretty useful for a large class of Python programs. The key thing, like win for mypyc compared to at least most of the other kind of competing products like Python, is that first like integrates with mypy. So you get like full type checking, type inference, everything. So using the standard type hinting syntax and semantics. And also if you're already using mypy, then it's kind of nice because then it's one-to-one kind of match. That's the first benefit. Compared to Python, it kind of doesn't have like it doesn't kind of do as good job, in my experience, of like type inference and like supporting like pep5 and like future peps. So that's, and the other one is it doesn't have any kind of low-level unsafe features, or at least those should be, if we add those, they will be kind of similar to like Rust. You have to kind of use some unsafe thing to enable it. So that is, this will be like memory safe. So you can't have like C pointer like in Python. So I mean, kind of everything translates to Python semantics. In Python, you can write stuff that's, you can't run it as a like normal Python code. So I guess like I see Python as the kind of main alternative at the moment. So those are things like it's kind of just regular Python. So the idea is we can make kind of code that looks like regular Python. It's not any more difficult to maintain than regular Python. So mypy was originally just a normal Python code base. It was probably like 50,000 line at that point, and it was pretty easy to migrate to mypyc. In part because it was already using static types everywhere. So because static types kind of restrict the kind of crazy, well, interesting kind of dynamic stuff you can do. So it makes it easier. But yeah, if you use a lot of like meta classes, like all kind of dunder methods and stuff, then the migration will be harder. But you can still kind of do it, but then you kind of lose some of the performance because then you have to fall back to like normal kind of Python CAPI stuff. The CAPI lets you do pretty much almost anything that you can do in normal Python. But things like if you just use C API instead of just using like, low-level C operations, then you lose a lot of performance. It might actually be slower than regular Python. Because C API, as I implied in the past, sometimes add overhead compared to the interpreter.
Thanks.
You mentioned at one point that if you take a function as a value, you just get the Python wrapper for that function.
Yep.
I was wondering, does mypyc have any kind of like optimization pass where it tries to do like devirtualization to avoid that extra wrapper whenever it could possibly be avoided?
Not right now, but there are various ideas about how to do some of that. I think the most likely way I would do it is to have a way of unwrapping the wrapper function so that you can, when you use it and like, say, add like a function to a list and then you get it back in mypyc code, and mypyc can then see like, hey, this function actually has the exact right signature, so that you can like unwrap that into a C function pointer, again, from the wrap function. But this is not, nobody's even started implementing this, but the general idea seems feasible.
Thank you.
Thank you so much for the great talk. Does mypyc allow you to have truly private variables within a module? As in, can you, because you end up with a C extension where you could have private things, can you basically stop stuff from being exported that you don't want it, that's not in dunder all or not like, or doesn't start with an underscore or whatever else?
Not at the moment, but it's again, like, this is something that, because it's compiled to C, we could support that. It just, there's so much other stuff, so it's not the highest priority thing, but we might get to it. I think one thing what might motivate us to do it is right now we can, like the Python wrappers are generated for every single thing, which means that the code that we generate is super verbose. So it might be useful to have a way of saying like, hey, this is the public API of the module, and everything else is kind of internal.
Right,
like
you don't need the like function wrapper or everything if it's not being exported.
Yeah, that's right. It will probably would improve like the import speed and etc. So Python kind of lets you do it. You can declare for each function whether it's like C only or Python or C and Python. So we could have something like that.
So as I understand, mypyc has the ability to, you can have like a class you're compiling with mypyc and then write like a normal C Python class that subclasses it, like the allow interpreted subclass.
Yeah, that's possible. It's not enabled by default, but you can have like a class decorator to enable that. Because if you do that, then it adds some overhead.
Yeah.
So we kind of do like a class hierarchy analysis, by default, by default that's not possible. So we can say like this method is never like overridden, so we don't need to use like, normally use like vtable column method, but then if there's no overrides, then we can actually just call it as like a C function directly.
Thank you.
Can you hear me? Okay. Have you considered some kind of interface? There was a package at the last PyCon where they were doing like GPU speed up, and if it didn't work on the GPU version, it would fall back to kind of the reference implementation. I think something like that here would also be helpful, just because I don't know. I mean, I get it's a compiler, so it'll tell you if it's not going to work initially, but it just seems like I can't drop this into a large code base and just expect it to work.
Do you mean, so right now what you can do, there are a couple of things I think it might help. So first you can only compile, say, like one module in a large code base, and generally you can then seamlessly use that from the rest of your code. So it just kind of exports the exact same interface as like the original Python. It tries to very hard. So you can access all the functionality from CPython. Minus things like if you have like subclasses, then you have to do. So you might need to add some declarations in some cases, but generally that's the first thing. Like just compile parts of the code and then add more files to the build gradually. And maybe you only need to compile, say, like 10% or less than your code, because usually in many programs, just a few modules are really performance sensitive. For the rest, it doesn't matter. So then you can just not compile them. So that's kind of one thing. And second thing is you can declare, that's going to in the next mypyc public release, there's a way you can declare a class as like a dynamic class, or non-native class, which means it's compiled into a regular Python class. So you can do all like monkey patching and stuff, kind of, it's more flexible. So there's like a way out of this, some of these static things. So you can kind of, the idea is that when you're compiling stuff, it's like, hey, use a meta class. You can't use a meta class if you have like this native efficient class, but then you turn it into a normal class. That's probably we can do it automatically. But the idea is the same, that you can kind of reduce the level of staticness but only when you actually need it, so that you don't, by default you get like good performance, but then you can kind of make things less performant but more compatible when needed.
Yeah, thank you. I have one follow-up. So when you were using this on the MyPy code base itself, were you just like profiling the whole code base to find the hotspots and then trying it on those files? Like what was your approach to saying this could benefit the most from compiling?
So the goal was to basically compile everything pretty much from the start. So basically we started with compile the key bits, and then we're going to add more files to the build until we were able to compile everything. So that was how it went, because we knew that mypyc is kind of unusual, that it's if you look at the profile, it's spending like this kind of, hundreds of relatively hot functions. It's kind of, there's a lot of logic, not like us. So I could say probably were some bottlenecks that we kind of fixed in the early days. I don't even remember what it was, but basically soon enough the profile was pretty flat. So we kind of then moved on to compile everything pretty much, except for like a small number of modules. But if you have a larger code base, then it's probably not practical. Then yeah, I'd use profiling, and then that's kind of the recommended approach. Yeah, first profile your code, see where you're spending the CPU, and then if it's only like maybe it's just a one module, and you just compile that one module, set it to C extension, and that might be all you need to do. But it really depends on the exact details of your workload.
All right, thank you.
Okay, I think that was final question.
All right, much better. Yeah, so I want to structure this by going through some of our key design goals that we've had for TY. And briefly, those are, we want it to be fast, we want it to be lazy and incremental, we want it to be informative, gradual, and expressive. So I'll go through each of these and talk a little bit about what that means to us in practice. So the first one here is probably no surprise to anyone. We care about speed. This is a pain point that we hear a lot from Python typing users, especially with very large code bases. We hear from some companies who have their developers waiting like 20 minutes to get full type check results on their code base. So how can we improve on this? Again, probably not a surprising answer. TY is written in Rust. For type checker performance, the implementation language really does matter for a lot of the reasons Jukka referred to in his talk. Type checkers allocate lots of data and build complex object graphs, and it makes a big difference to use a language that lets you lay out your data in very cache-efficient ways instead of chasing pointers all over the heap. It also makes a very big difference to be able to parallelize work across multiple threads because type checking, a lot of type checking is very parallelizable. And so to be able to make use of all the cores in your machine, and Rust also allows us to do that. So it's still early days still for TY, and relative performance is hard to talk about because it can vary a lot by project, depending on the details of the project. But in general, our experience so far is that TY is typically 1 or 2 orders of magnitude faster than current generation type checkers. So the second goal, closely related to the first, is that it's important to us for TY to be lazy and incremental. So we want it to not only be fast on a from-scratch check of your code base, but also very low latency in an editor environment where you're making changes. So in that scenario, you're likely making many small changes to a small set of files in potentially a very large code base. So even if TY is very fast in general, on a very large code base, it may still take tens of seconds potentially to recheck everything. And that's still far too long to wait after a change in your IDE. So we want to be lazy, which means doing as little work as possible to give you the information you need. And we want to be incremental, which means when you make a change, we reuse as much as we can of the information we previously had and recompute as little as possible. It also turns out to make a really big difference at what granularity we are lazy and incremental. So in a typical large Python code base, the module dependency graph tends to be quite tangled with cycles, etc. So in this particular example, if you change these 3 blue files, the module dependencies would tell us that all of these files in yellow now need to be recomputed, which in some cases can be quite a significant proportion of the entire code base. So let's look at an example of 3 specific modules where we have main importing inter, importing core. So if TY is asked to type check main, we'll see that it imports C from inter. We'll go evaluate only that visible binding of C over in the inter module. We will see that that depends on A and B, so we'll evaluate the bindings of A and B, and that gives us everything we need to type check main. We'll never look at D at all. We'll never look at core type. We'll never look at import, and we'll never evaluate anything in the core.py module if you've asked TY only to type check main. And on the flip side then, if we've evaluated or type checked all 3 of these modules, and then the developer makes a change in core.py, we will understand that we only need to reevaluate some parts of inter.py, and we won't actually reevaluate anything at all in main.py. So even though there's a module level import dependency all along the chain here, being more fine-grained allows us to break up those dependencies and do a lot less work. And this fine-grained laziness also, maybe counterintuitively, it turns out to make us a lot faster when checking your entire code base. Because even if we're checking your entire code base, likely in a large code base, you have many third-party dependencies. And some of those may be very large and have very large modules. And if you only import and use a small percentage of what's in those very large modules, we will only evaluate a small percentage of that third-party code. The best way to be fast is to avoid doing unnecessary work. So that can save us quite a lot of time. Okay, third goal. We want TY to be informative. So that means that errors, when you get them, diagnostics, should give you all the information you need in order to understand what the problem is and fix it. So here's an example of the way a diagnostic looks in TY today. If you have in lib.py, we have a function defined multiply, and we call that function from main.py with an incorrect typed argument. So TY will give you code frames showing the relevant code in both modules, saying here you have a problem in main.py, you've passed the wrong argument type. here's where the function is defined, here is the parameter that you passed the wrong argument type to, etc. Okay, design goal number 4. We all know Python is gradually typed, and we know roughly what that means. It means not everything in your program necessarily has a static type or a type annotation. But can we state in a more precise way what it means for a type system to be gradually typed, or a type system to be gradual? There's an invariant called the gradual guarantee in the gradual typing literature. The gradual guarantee says that removing a type annotation should not cause a new type error to appear. Or flipped around the other way that may feel more natural, you shouldn't need to add type annotations to your code base in order to get rid of type errors. Or another way of saying this is, the type checker shouldn't make assumptions about your intent where you didn't clarify it with a type annotation and then emit diagnostics based on those assumptions that may or may not be accurate. And historically, the Python type system, although it's gradual, has not consistently prioritized the gradual guarantee. And one consequence of this is that the typical experience has been that if you have a large untyped code base that's working and you run a type checker on it, you will often get many, many type errors on the first run. And in many cases, that's because the type checker is making unwarranted assumptions about your intent in untyped code. And then you have to start adding type annotations to correct those assumptions and get rid of those type errors one by one. And of course, many of us in this room have gone through that whole process successfully and gotten a lot of benefit from type checking, and that's great. But I've also seen that experience, that on-ramp experience, turn a lot of people off of static typing in Python. They have a working code base and they run the type checker and they say, what's this? My working code base has like 1 million type errors. Why is that? And so one of our goals with TY is to see if we can turn that knob a little bit in the other direction and improve that on-ramp experience. So that was very abstract. Let me talk about a concrete example. So here we have a class retry policy with an attribute max retries equals none. We'll create an instance of retry policy. We'll reveal type on policy.maxretries, and then we'll try to assign 1 to policy.maxretries. So if we look at the behavior of mypy and pyrite here, they're both in agreement that the type of maxretries attribute is none, which seems reasonable. That's the only thing we ever saw assigned to it in the class. And so they're both also in agreement that it's an error to assign 1 to none. And so you can't say policy.maxretries equals 1. But should this really be a type error? The code on the left is untyped, has no type annotations. The developer hasn't made any assertion about what types are valid to assign to retry policy.maxretries. All they've done is assign a default value of none to it. If the intent of the developer was always that it should be an integer or none, that code is perfectly fine and type safe. So this is an example of where the type checker has made an unwarranted assumption that the intent of the developer was that this attribute on every instance of retry policy class should always and forever be only none, and then issued a diagnostic based on that assumption. And we can see that this is an example of an assumption that violates the gradual guarantee, because we get this error. If we go and add the annotation int or none to that attribute, the error goes away. Now the type checker is happy. And that's exactly what the gradual guarantee tells us should not happen. So going back to the original untyped code, let's see how TY handles it. We don't infer a type of none for max retries. Instead, we infer a type of unknown or none. Unknown here, if it's not familiar, it's actually the same type as any. We distinguish in the same way as Pyrite does between an any that comes implicitly from the lack of an annotation versus an any that comes from an explicit annotation with the any with typing.any symbol. So in this case, this just means we infer the type of max retries to be the union of unknown or none. So what does that mean? It means that as far as we know, the intended type of max retries could be anything because the developer hasn't given us any explicit declaration of their intent of what the limits on its type should be. But we do still know the or none part. We do still know that it could at least be none. That is definitely a possibility for what it could be. So because of that, we won't error on this assignment policy.maxretries equals 1. That is assignable to unknown or none. but we also haven't thrown away the information we do have. So if you try to do something that wouldn't be valid for none, like for instance, try to add the string foo to an instance's max retries attribute, that none plus foo, that's not valid. So we can still error on that because we know none is a possibility. So I'll mention one other example of where we aim to be a little less opinionated than current type checkers. We are explicitly okay with shadowing the same name in a scope with a new declared type, as in the example shown here, where this function accepts a string and then wants to immediately convert it to a list of strings by splitting it. This code works fine, it's type safe, it's even idiomatic in untyped Python code, and we prefer that if you're adopting a type checker here, you don't have to pick a new variable name just to make your type checker happy.
Are you going to bring that up with the typing council to somehow make that?
Yeah, so all of these things that I talked about under gradual are like, so the question was, are we going to bring this up with the typing council, which is a good question. All of these things are things that are currently not really specified in the typing spec. So it's more, maybe the typing council should try to specify some of these things, and then we need to have a discussion about how they would be specified. But yes is the answer. I think we should have those conversations. And also about this next section. So lastly, we want TY to help push the envelope in making the Python type system itself more powerful and expressive. So one of our primary innovations or investments in this area is that we're the first Python type checker I know of that has first class intersection and negation types. That could be wrong. If somebody knows of another one, I would love to hear about it. So this could be the subject of an entire talk on its own. I won't get very deep into it. I'll just give one quick example of where first class intersections help us deliver useful features more easily. So start with a simple example. We have an empty class. We have a function that takes an instance of that class. Obviously, that instance has no X attribute, as far as the type checker knows. But if we check hasAttr for that attribute, then inside that check, TY knows that the attribute exists, gives it a type of object, because we don't know anything more. This is nice, but it's also a feature that mypy has, so this is not something new. What's a bit different is how it's implemented in TY, and this does have some consequences. So in TY, all of our type narrowing, where you do an if check, if is instance, or whatever kind of if check, and then we have a more precise type after that, all of that type narrowing is implemented by creating an intersection type, intersecting the prior type of the name, and the whatever type can be determined by the is instance check or whatever check you did in the if statement. So yeah, and then we simplify that intersection type according to a generalized understanding of subtyping and type disjointness. So we can see here that TY actually describes the type of object after the check as an intersection of C and a synthesized protocol type. Oh, I left the wrong name in there. It's not spam, it's X. But yes, C and a protocol with one member. Oh, I failed to change two things in that slide. I apologize. Should be empty and a protocol with members X. Apologize. Yes. Okay, let's expand the example to clarify why this makes a difference. Here we have a class with X that has an attribute X and a final class other. And our function takes a union of with X and other. And if we do a hasAttr check on X, within that block, TY now actually narrows the type all the way down to simply with X. Other just goes away. And now we know the type of this X attribute is int. And this is something that mypy's implementation can't do. And the thing that's interesting about this is that we never thought about this case in the implementation. Alex implemented hasAttr narrowing on a whim earlier this week. It was a 10-line diff. I mean, all it involved was synthesize the protocol type and intersect with it. And all of the rest of this behavior just totally fell out of our existing understanding of how this protocol type interacts with all other types in the type system. So for instance, what's actually happening here under the hood is we have the type with X or other. We intersect it with this synthesized protocol with one member. We distribute the intersection across the union. So now we have the intersection of with X and the protocol, and we have the intersection of other in the protocol, and we have the union of those two. And the first element there simplifies to just with X. because with X is a subtype of the protocol. The second part simplifies to never, because we know that other can't have subclasses, and we know other has no attribute X. And so that simplifies to never. The union of with X and never simplifies to with X, and we get this behavior out of it. Okay, so that covers our 5 design goals for TY. Before I wrap up, I should clarify the current status of TY with the big yellow warning triangle. TY is pre-release. It is not ready for production use. It's missing features. It has bugs. It might even crash. We are working to make it more stable and more complete. But all of that said, it is still fun to play with in its current state. So we're happy for you to give it a spin. We're developing it fully in the open. We take lots of pull requests, and we would be happy for your feedback. So you can give it a try. It's really easy with UV. You can just do UVX-TY check in any Python project. Or you can try our online playground at play.ty.dev. Or you can install our VS Code extension, which is also very much a work in progress, and send us your bug reports and pull requests. And I think, since we're running slightly ahead of schedule, I'm actually going to take 1 second here to do a quick demo of the playground before I'm done. If I can find...
Please don't do generics.
Well, I could do some generics. Okay, it thinks that monitor is on that side. That's confusing. Okay, here. Okay, this one's just totally for fun. Oh, wait, you can't see this because I'm on the wrong screen. Let me go back to mirroring just to make this simpler. Where are we over there? There we go. Okay. Do I need to make that bigger for you all to see it? Yes. How's that? Okay, so as far as I know, we're the first Python type checker that can solve Diophantine equations. So you simply provide a list of all natural numbers here, and then TY will tell you that the type of this expression here is bool, which means that solutions to this equation do exist among the given natural numbers. And over here, TY will tell you that the type is literal false, which means we can't find, we can't confirm Fermat's last, or deny Fermat's last theorem among these natural numbers. Down here, we find, again, a type of bool, meaning that we did find a solution to the Catalan conjecture within those first 13 numbers. So that's kind of fun. What do we have here? This is the example I had before. Oh, this is maybe just interesting to show. Some of you may have thought of this already, but if we don't make other a final class, then the revealed type down here is a little more complex. It's now the union of with X and the intersection of other and this protocol, because other could have subclasses which might have an X attribute, and we don't know anything about what that might be. So now the revealed type of X is object instead of int, because we have no information about what it could possibly be. We also have this run thing over here. I think it uses pyodide to actually run your code in the playground, which is kind of fun. I don't think I have a good example here for demonstrating that right now, so I'll skip over it. And then the last thing here that's fun in the playground is it's a multi-file playground, which is really nice for doing like reproductions of things involving imports and whatnot. And this is set up to show a kind of a neat feature where I think in existing type checkers generally, like knowing that if you do an if sys.version info is less than or greater than something check, it's like a fixed recognition of a certain pattern in the AST, and if your check doesn't exactly match that pattern, the type checker just won't understand it at all. In our case, we do those evaluations using actual type inference on the actual expression. So a simple example of that is here if we have a new shiny variable that we assign to a check of the version, and then over in some totally different module, we import new shiny. We'll find that new shiny has a type of literal false, and that's because here in my config, I said we're on Python 3.11. And because new shiny is false, we know that X here has a type of literal 2. It can't possibly be 1. And if I go into the config and say, no, we're actually on Python 3.12. Now we know that this is 1 instead of 2. And we know, we understand which path had to be taken here. So I think that's all I have for the playground. And I will just pitch one last thing, which is that if you want to talk to us more about TY, if you want to share your hopes and dreams for the Python type system, or get further into the weeds about TY's architecture and implementation or design choices, we would love to see you tomorrow at 10 a.m. in room 316 for an open space. Thank you.
Oh, thank you. I assume from you said you had a VS Code extension that it will also operate as a language server, like LSP server.
Yes, that is certainly part of the vision. The current VS Code extension will give you type diagnostics. It'll give you go to type definition. I think that's all it will give you at the moment, so it's certainly far from feature complete. But all of that stuff will be coming.
Okay.
Can you still choose to disallow name shadowing?
Well, let's see. No, but name shadowing does. So here, let me use the playground here since we have it. Let's open a new tab. Okay, the internet might not be. Okay, never mind. Let's use an old tab. Nice thing about Rust is we can compile it to WASM. So once the playground is loaded, the type checking is just like super fast because it's not having to. It's just running the Rust code in WASM. Okay, so to give an example of the shadowing, if you say here that X is a string, yeah, def, sorry. Then you're certainly not allowed to do this, right? That's an error because you're assigning an integer to something that you said is a string. So that kind of shadowing obviously is not sound and not allowed. But if you say, no, actually, I really want X to be an integer starting now, if you say that explicitly, then that shadowing is allowed. We don't currently have a way to disable that. I mean, the longer term vision for TY is that it also becomes the foundation for a type-aware linter, like the next generation of rough. And that's the kind of thing that we would envision putting in a lint rule, not in the type checker. If you want to have a policy that says no declarations or no redeclarations, that's easy enough to put in as a lint rule for your code base.
Just on this example, what if you delete X?
I don't think we have any special handling for delete built in at this point. I mean, so this is sort of outside the type system in a sense. This doesn't change the type of X. What it does mean is that we have a pretty good understanding of flow control, and we can usually tell you, we can definitely tell you if a name is not bound. We can often tell you if it's possibly not bound, although that's very hard to get fully correct because there's lots of different patterns within variance that are hard to understand. But in this case, I don't think we've done it yet, but we would ideally just give you an error here that you're using an unbound name. And that wouldn't be that hard to implement. Del is very uncommon, so it doesn't come up a lot.
Still this example, sorry.
Yeah.
Yeah, why does redefining X without an annotation not still succeed, like by means of the gradual guarantee?
I don't think it violates the gradual guarantee. Well, that's an interesting point. No, you have a. That is a good point. You can, in this case, fix a type error by adding an annotation. I think the difference is that only occurs when you have another annotation. Like, if this is unannotated, then we're fine with you doing x equals 1, and then we're fine with you doing x equals foo. There's no point at which, if you haven't annotated the type of x, we're never going to complain at you about something that you assigned to x. And it's not like we don't understand x here. Like, we understand perfectly well that x is the string foo here, and we understand perfectly well that x is literal 1 here. So we have flow-sensitive type inference of what the actual type of x is, but we have no restrictions because there's no annotations on what you can assign to x. So once you've said that X has to be a string, you have declared an intention. And if you want to change that intention, you need another annotation to do it. So I think that's a little different.
It's thin ice. I think we found a counterexample to how intuitive the gradual guarantee really is, because if it did allow you to do X equals 1 without complaining, you would be very unhappy about your type.
Oh, for sure. Yeah.
So
yeah.
there's some contradiction here.
Well, the gradual is only going backwards from having types, right? Not going forward and adding them. So if we start with
So it can go from having some types to having more types.
Yeah, I mean, I think, yeah, you could argue that. I think in terms of the intuitiveness, the fact that you have started annotating what the type of X is, I mean, local names are funny because they occur in multiple places and you can assign to them multiple places and you can have multiple annotations for them. So I do think it's different to say we aren't going to, if you remove all of the type annotations on X, that's not going to create a new error versus saying, well, if you have 3 different type annotations and you remove one of them, yes, that could create an error. But yes, we can discuss this more at the open space tomorrow.
Great talk. I liked your point about the intersection types and having them be first class. Is it possible or any plans to write user-defined intersection types?
So, okay, since I'm here in the playground, this is something where I don't think we've made a clear decision yet about whether or how much we want to expose this before intersection types have been standardized, but it is there. We don't have. I mean, we're not changing the parser or not changing like the runtime or anything at this point, so we don't have nice syntax for it. But if you want to play around, here, can I get rid of this? If you want to play around with intersection types in the playground a little more easily, we have this kind of thing. So you can say, give myself a couple classes here. Actually, let me give me some attributes on them. Oops. And then I will say, I have a function here that takes the intersection of, brackets, C and D. And then what can I do here? I can say, oh yeah, man, live coding, so much fun. Okay, I'm going to reveal type of, I can reveal type of obj, and we'll get a nicer syntax than the one I had to write. And I can reveal type of obj.x, and that's an int, and I can reveal type of obj.y, and that, if I scroll down, is a string. And then if I want to go one step further and say, well, I have another function here that takes something that has to be a C, we can go ahead and call that function from up here, and that's fine. And if I also say this has to take a D, actually, that's also fine. So, obj is both a C and a D and can be used anywhere you need either one of those. So, yeah, so the answer is, we do have a way for users to denote intersection types already. So the main question is, do we provide a runtime shim for TY extensions? Right now we use it a lot in our test suite, but in order for users to really be able to use it, it would have to not fail when you do this import at runtime. And that's not something we haven't taken that step yet.
Yeah, sorry. So obviously this is a rough application, so you're not tied to the Python interpreter. Do you do some Python environment detection or stuff? And specifically to that, I assume you're still using the TypeShed project for the standard library?
Yes.
And do you have any plans on how we should, as we start adding type annotations to the standard library, how we can kind of like solve not everything is in the TypeShed module, or how that could work?
Boy, can I call that question off topic for the talk? Because I don't want to answer it. I think it's a very complicated topic, adding type annotations to the standard library. And I think the typing that we've come to rely on from TypeShed would in many cases be so difficult to reflect in a backwards compatible way in inline annotations that I don't know that I see that happening anytime soon. I mean, we can work on it. It's a big problem.
Do you detect the Python environment, or like how do you detect the Python environment? Because now in that one you hard coded into the configuration,
right.
But if I'm running locally and I don't have that hard coded, like how do you determine what Python I'm even targeting?
At the moment, Alex, correct me if I'm wrong. I don't keep up with all of the PRs. At the moment, you have to say it in your configuration or on the command line. No, no, we detect it from your virtual env. Yes. So we will find your virtual env, like if your virtual env is activated, like the virtual underscore env environment variable is set, which is set by most of the project managers like UV and Poetry, et cetera. Then we will detect your virtual env from that. If you have a .venv in the project, we'll default to that as your virtual env. You can also specify your Python interpreter or environment or installation to use. And any of those cases will detect the Python version. Is that right? Or some? No. Not quite right. Oh, sorry. Come talk to us afterwards. Come to the open space and you can talk to the people who actually know those parts of the system.
We've implemented a very minimal Python environment detection interface because we don't want to reinvent the world there yet.
Yeah, there'll be more coming there.
I assume you still bundle the type shed into the release of the TUI, no?
Yeah, so TypeShed is like bundled directly into the Rust executable that we build as like an embedded zip file. We also have an option where you can specify a custom TypeShed on disk if you want to mess around with your own TypeShed for some reason.
Hi, one thing I was wondering is what is your guiding principles for how you actually format the error message? I know sometimes with other ones I can get confused if the error message is very complicated.
It's very hard problem, just because there's a balance between you really want the error to give all of the context that the user needs to figure out what's going on, because it can be a lot of digging in some cases if there's an obscure error message to figure out what's really going on, and we really want to make that transparent. But in some cases, the trade-off is then there are these pathological cases like, I don't know, the POW function in TypeShed has 13 overloads, I think. And so you really have to, what? More than 13, a lot of overloads. It's Alex's fault that it has a lot of overloads. So you have to think about like how many pages of diagnostics do you want to pay for one bad call to POW in order to give all this context. And so it's a really hard problem to like figure out exactly how to narrow down the really relevant context.
We actually have a great diagnostic POW now.
We have a good diagnostic. Do you want me to show it?
Yeah.
Okay. Let's see.
Yeah, not on the playground. Terminal.
Oh, right. Of course, the playground won't be as nice. I don't need to show it. You can go try a bad call to POW yourself and admire the diagnostic. Yeah. Or we'll do it at the open space tomorrow.
Why won't the playground be nice?
Well, the playground we have like, even on the CLI, you can pass, if for some reason you can pass a flag to get concise diagnostics, which is more like current type checkers where it's kind of like all in one line, one line per diagnostic. And that's what we get in the playground, is that same concise format down here. Like we don't have this kind of diagnostic that I showed. That's a CLI thing, like with all the code frames and everything.
So I ask because is the output in the playground similar to the output that you would get in an editor, or is the output you get in an editor similar to what you get in the CLI? Because when I'm writing TypeScript in VS Code, it's horrible. The diagnostic you get back without having to add extensions or whatever to try and clean it up.
Yeah. I think today the output you're going to get in VS Code is going, or actually I mentioned the VS Code extension. We do have a language server protocol implementation, and you can use it with any editor that can handle the language server protocol. So I shouldn't act like it's only VS Code. But I think today the experience you'll get through the LSP server is the concise diagnostic. That's something we'll probably iterate on over time and see. I think it's a different environment than the command line, so it's never going to be one-to-one, but obviously we want to provide as good as we can through the LSP as well. Yep. Question over there, one there.
Hi. So I know kind of like a big problem in larger code bases that, have either never had types or have very limited types is adding types by hand. People like go through and, have a lint ticket for a sprint or whatever and add types. Yeah. Is there any possibility of having TY add types for you? Like when it can be, sure, can it just go through and add types? Like I know Instagram had monkey type where it would do it at runtime, which was awesome, by the way, for anybody that worked on that. Thank you. You saved my butt on a project.
I wrote that.
Did you really? Oh, thank you. Yeah, that saved my sprint one. Thank you. Something like that where, TY could go through and, annotate everything for you and actually make edits to the.
Yeah, for sure. I mean, it's not there yet entirely. It's something we want to do for sure. Like you already probably saw in the playground here, like if I say x equals 1, the playground will like put in this gray text here that tells you what the inferred type is. And the same thing will happen in like VS Code. We haven't actually done this yet, but it wouldn't be a hard PR to enable the thing where you just click on that or double click on it and it just inserts that into your code. So that's one form of doing that. That's not like a bulk way of doing it, but certainly other tooling to do it more in bulk can be built for sure. I don't know where it's going to come on the roadmap. We have a lot to do, but.
Could you make it a lint rule?
An autofix lint rule, and potentially.
Yeah, we actually already have some of the rules that can do this to an extent.
Yeah.
That generally just do very basic touches with the top module. But yeah.
A question about gradual typing. So if a code base with few annotations can be type checked initially without errors, how do you know where to add new annotations to improve type safety?
Yeah, no, that's another thing that I think we would like to see handled via lint rules / additional tooling on top of the type checker, right? Like the type checker is going to try pretty hard not to give you false positives by default. But if you want to say, tell me everywhere that you're seeing an unknown type, that's something that can quite easily actually be built as a lint rule on top of what we already have. We can just go check the types of all the expressions. And I mean, there's some work to make it nice, but that's how we would envision handling that kind of use case.
All right, so there's another language server / type checker written in Rust.
Yeah, you're about to hear about it in the next talk.
Okay.
Yes.
Maybe I should save my question until then. I saw their talk yesterday as well, and I'm still not really clear on how TY and Pyrefly are different.
Boy, that's a big question. I think probably the best way to answer it within our time constraints is that you can try them out and draw your own conclusions about how they're different.
Thank you.
Howdy. Hey, works. Any thoughts or considerations on like the pluggability of the cache, specifically in like a remote setting? So if you join a new company in that giant monorepo, you're not bootstrapping that cache from scratch.
Yeah, so I mean, persistent caching is something that's on our roadmap, but we don't have at this point. At this point, like when you first fire up your editor or first run it on the command line, we have a watch mode on the command line too, so you're going to be doing a full type check. I mean, TY is fast enough that we certainly like to have persistent caching, but it's not as high priority as it might be because even on the biggest code bases, like internal company code bases that we're able to look at, it's still like a matter of seconds, not minutes, to do the whole check. So it's like you can probably handle that when you first open your editor.
Have you compared that to PyRack?
Yeah, I mean, it's quite a bit faster, like order of magnitude faster.
Sorry if it's an implementation detail, but what do you use as the format for those caches? Is it like, I assume it's not like a SQLite type thing, but what's the binary format for the?
The persistent caches don't exist yet.
Sorry, the cache. The
in-memory caching. Yeah.
It was only in memory.
I actually have a slide about that, which I was going to skip, but since you've asked, I can show it. You've given me the excuse. Yeah, so we use a library called Salsa, which is a generalized framework for incremental computation. It's a Rust library, Rust crate, that is also used by the Rust Analyzer project, which is one of the language server implementations for Rust. And the way Salsa works is that you structure, the type checker is structured as a set of what are called query functions. So you define them like this in Rust. You say, I want Salsa to track this function. And so every function like that takes a Salsa database as an argument. And then it takes like, so I talked about how we're like granular at the level of individual bindings or definitions. Like we'll go look at one binding or definition of a name. So you can say, we want a type for this definition. You pass in the definition and you get back a type. And so if you do this, then Salsa will automatically, without you doing anything else, memoize what the type for that definition is. And whatever the body of this function is, whatever code that executes, Salsa will keep track of what other Salsa queries you've called in the process of computing that type. And so it can build up this dependency graph of what all depends on what. And it really helps us avoid having incremental correctness bugs, because we don't have to implement any manual sort of cache invalidation like, oh, if we change this, then this has to be changed. All of that is just done completely automatically behind the scenes by Salsa. So when we say this file changed, Salsa will just through the whole like dependency graph that it knows about, and it will just mark all the queries that have changed as changed, and the next time you ask for them, it'll rerun them instead of just giving you the cached value. So that's and I mean, I make it sound really nice, and it is. We think that sort of like guarantee of incremental correctness is super important, because incremental cache invalidation is just super hard to get right and super hard to catch when you haven't gotten it totally right. But there's also trade-offs and costs to this. It can be hard. I think we spent a lot of time in the development of TY, like fitting the type checking problem into the shape of Salsa, adding support for resolution of cycles to Salsa. So it's definitely trade-offs, but we think it's worth it. I mean, there's some runtime overhead to Salsa, but we gain that, from what we've seen, we gain that and more back by being able to ignore large chunks of third-party modules that don't actually matter to your project. So like trade-offs both ways, but this is how we handle the problem. Okay.
So given that you run with completely unannotated code, say you have def f of x return x plus 1, and then you call f of hello.
This sounds like a playground problem. Say that again.
Yeah, so say you have like def f of x return x plus 1.
Okay.
And then you say f of hello, like.
No, so our type inference, as is mostly the case for most Python type checkers historically, is at function boundaries, right? So the type that we have for x within the body of f is unknown. So we're not going to error on this code. Now, Pyrite does do some like inlining of small unannotated functions, and that's also something that we would like to do. We don't do it yet. We have a PR up for doing return type inference. So we would at least, like, if you did know that this was an int, and you'd say, what is the type of f of whatever, we would be able to tell you, oh, we looked at the body and we can see that it returns an integer. So that's something that we will have as soon as I get around to reviewing that PR.
But you don't plan to like infer a has plus int protocol for x itself?
That's not something we've discussed doing. I think we'd have to evaluate the trade-off of complexity versus benefit in practice. Yeah.
Yeah, I was a little confused about a previous example you had on the playground where you said x equals 1.
Yeah.
And it annotated it as a literal 1.
Right.
Okay, doesn't that make it constant?
No. So I guess implicit to TY's model anyway is the distinction between a declared type and an inferred type. So the declared type is like, what is the largest possible type that this variable is ever allowed to contain. And in this case, because there's no annotation, that is unknown or object, I forget. I mean, it's like, there is no limitation. You can assign anything you want. You can go right ahead and do x equals foo in the very next line because the declared type places no restrictions. But we also have an inferred type, which is what is the most precise knowledge that we can say for sure about the type of this name at this point in code flow. And so in this case, we have an inferred type of literal 1, and then we have an inferred type of literal foo, and whatever you do with x, we might have a different inferred type down the line. Does that make sense?
The user experience of that kind of inference is horrible. Type right. Pyrefly does it, and it is never right.
We look forward to your bug reports. I think we might need to move on to the next talk. Yeah, I'm sorry. Come to the open space tomorrow, and we will be happy to talk more about TY. 10 a.m., room 316 tomorrow.
Okay, hello everyone. I'm still Stephen Troxler, and I work at Meta, and I'm on the Pyrefly team. And we wanted to talk a little bit about what we've been up to and why with Pyrefly. So Pyrefly is a Python type checker. If you want to learn more while I'm speaking, you can go to pyrefly.org and read about it. So first I'd like to address why we're doing this. As many of you probably know, we already have a type checker at Meta, Pyre, which we're using today. But we found that it was not meeting all of our needs. Probably the biggest pain point we encountered was that it's too slow for IDE use cases. It was designed to bound batch compute. In particular, it was designed as part of a project to build a static analysis tool. Those are typically very long-running processes. And we made it faster, but we just never got the kind of speed that we want for IDE use case, where it should be not perceptible to reanalyze the code after it's edited. There were also bugs in the language logic. In particular, the name resolution had issues. And both of these problems were kind of pointing us toward a substantial rewrite of what was going on. We needed to change the architecture to get the kind of speed we wanted in the IDE. And we needed to kind of rebuild most of the analysis if we change name resolution, because most of the analysis depended on the existing name resolution. We thought about rewriting it in place. It's certainly possible to build a great type checker in OCaml, which is what Pyre was written in. That's what Flow is written in, for example. But there were a number of challenges that moved us away from that. One of them is that getting full Windows support on OCaml is a challenge. It is possible, but it's not the easiest thing. And we really want to support both open source users and internal users that require Windows. We also wanted to really be more part of the community than we had been able to be. OCaml is not a difficult language necessarily to learn, but you have to be motivated. And I think it's fair to say a lot more Python developers are excited about learning Rust. And in fact, it's much easier to use Rust in Python programs because you can write extensions in Rust. That's not convenient to do in OCaml because then you have two garbage collectors. So to be a better part of the community, we really wanted to use a language that more people are using. And lastly, internally, the tooling story on a language like Rust that has a large pool of developers already and it's rapidly growing is much better. Everything works out of the box in our development environment. We always had to fight it a little bit with OCaml. We also looked at existing type checkers. At the time, TY was not really far enough along for us to evaluate. But looking at all of the others, we decided a deep integration into Buck 2. That's one thing we need because we use the Buck build system. Similar to Bazel, there are a lot of build rules. It doesn't run like a normal Python process, and you have to understand how the dependencies are laid out. We also are under particular performance constraints. We have large code bases, but I think that's sometimes understating it. What we really have are code bases with very large, strongly connected components of modules that can have at the typing level cycles in them. And we can be talking 5 digits worth of modules that need to be at least partially analyzed to resolve one IDE action. So we're really targeting a specific use case where we need speed on these large connected code bases. And last, because we're a pretty large company, we have other teams we're trying to work with that build tools that want information from the type inference system. So one of these is PISA, which is baked into the Pyre project. It's the static analyzer I was talking about that helps us find security bugs. And it will need to integrate with the Pyrefly type checker to get the type information for performing that analysis. We also have a code database called Glean, and the indexer that scrapes the Python code to fill out that database wants type information coming from Pyrefly. So that was another motivation, is to make sure that we can build the right APIs for those kinds of use cases. We hope that we can also build open source use cases. We had an issue already show up on our GitHub asking for this sort of thing. So stay tuned. We'll see how it is all built, but this is very much something we want to be able to support. With those kind of pain points and needs in mind, our goals for the project were to be fast by design for both the bulk type checking case and for the IDE case, and to be as bug-free as possible. So fixing all of those bugs that we were really having trouble getting rid of in Pyre. And another thing that we kind of shifted on since the design of Pyre was that we want better trade-offs on type inference, in particular, I guess, return type inference, which is something Pyrite has. We wanted that because we now have more and more developers, both internally and externally, that are working with less typed dependencies, but they want as good of IDE behavior as they can get. And especially in the case of getting things like autocomplete, the more return type inference we can do, the more we can give them in their editing environment. It's written in Rust. This is good for performance, and in particular, nice primitives around parallelization. And thank you to Astral. It's built on top of the rough AST, which has been a delight to work with. And something that Rust offers that was alluded to is there are incrementality engines available off the shelf. We actually opted not to go with one of those. We've kind of built our own system for dealing with the incrementality, focusing mostly on modules, but not invalidating too aggressively, but modules as the unit of analysis. A couple new ideas to highlight. One that also TY did, and we already saw a demonstration, is integrating an interpreter into the sandbox. That's been particularly useful, I guess, for me. I've done a lot of work on descriptors. It's very hard for me to look at a code snippet and be totally sure what happens, and being able to demo it in both a type checker and the runtime at the same time is handy. Another thing that we've been kind of focusing on is how the attribute API works. So again, it's built around the descriptor API from the start. This is something that in our experience, a lot of type checkers have kind of assumed attributes have types and then tried to edge case the descriptors. And that can be pretty hard to do. We design the API so it's always, you understand you have a base and you always have a get or a set action. And the way those resolve could involve method calls, could involve looking up overloads, all sorts of things could happen. So there are restrictions on the API you can use. That made supporting user-defined descriptors much easier. It also turns out to make some other things easier because built-in descriptors slot very well into the same API. You have class methods, instance methods, they all have binding behaviors that are different. But you can represent it very nicely using get and set actions that understand the base types. And a few qualifiers like final can also be represented this way, where you just say the set action is a type error. And the tricky edge cases that it doesn't help with are at least made obvious, like a little bit of an open question. We have an answer for now. But what happens, for example, if you try to narrow on a descriptor access? That's a method call at runtime. You really can't guarantee anything about it, and you have to make a decision about what kind of trade-offs you want to make here. I think the biggest innovation is actually not so much directly user-facing, it's just how we structured the whole thing to try to get the best performance on the types of module dependency structures we see, which was to break things into phases. This is not a totally new idea. For example, Pyrite has a binding phase, and I haven't looked in great detail, but I would kind of assume that TY must do something a little bit similar in order to provide the kind of laziness it does. We chose 3 phases, and each phase is about 10 times cheaper than the next phase. And the reason we chose 3 phases was to really break things up clearly. We have a definitions phase that's an AST scan, but it can skip much of the AST because it's only looking at top level, and it just says, okay, what are all the names directly defined in a module? And we can do that fully in parallel. Once you've done that, the next phase now doesn't have to worry about import star. That's really a big motivating factor. So in the next phase, we know exactly what every name refers to going through the import system, and we do all the control flow analysis. So that's a much more expensive phase. We carefully walk through the AST, we do a lot of work, but there are still no types, which makes it pretty fast. And at the end of this, we get a graph that I'll talk about more of all the computations we're going to need to do for type checking. And then we're able to type check, and we get as much parallelism as we can. It's not quite as simple once we get to type checking because you can hit recursive types and all sorts of more complex cases. The binding phase is really, at this point, I'm kind of going into technical details because that's how I decided I wanted to do the talk. But the binding phase is really, to me, the heart of learning to actually understand how everything is working. It makes a table of bindings for each module, which is just the graph that is produced from the control flow analysis. And there's a couple ways you can think of what these graph entries are. One way of thinking of it, we don't have a pretty printer, but it's sort of like an intermediate representation. It's pretty simple, similar to static single assignment, but it's only at the statement level. Expressions remain nested because it would have been a whole lot of work to make a full SSA, and it's not really necessary. Another way to think of it is that if I have a handle on a binding, then I have a handle on a lazy type. And from an implementation point of view, it means every time I would have liked to have matched on the type when I'm in the bindings phase, instead I need to store that reference, and then later when I get to the solver phase, I'm going to match on the type because I'll be able to get it at that point. And I just have a little example of how this works roughly. So we start with some namespace. We'll have things like int in it. I'm assuming kind of f was probably imported somewhere above. And the first thing we'll do when we look at this example is we'll see that we have an expression. It's a call to f. When we see a name in an expression, we'll look up the current binding. And this is really our context. We're doing an AST traversal. We have a set of bindings that's our type context. And we will create a use. So the key is use, and the value is a forward. Forward just means when I resolve this binding, just grab whatever is in the binding it's pointing at. And then we'll create a new binding for the x, which has been defined right here. And x is defined to be whatever the result of type evaluating the expression f is, or the call to f. Then when we get to the next line, we'll do kind of the same thing inside of the is instance. We'll find all the names, we'll create the use keys, and they'll be forwards to whatever's currently in scope. Is instance, though, we know is a narrowing operation, which means we now need to create new bindings for the result of the narrow, so we get a positive and a negative case. And when we enter the positive branch, the if side, the first branch, we'll know that the positive narrow is the one in scope, which means when we see x in an expression, we'll know to forward that particular narrowed binding. And then we'll create a def node for y. That's only live in this branch of the if. When we go to the else, we'll do something similar. There's no usage required here since it's just a string. Then when we get to the bottom, we will know about those two branches in the control flow. We create the phi, and y is available. And that's kind of how it works. The experience of working on this is really that I think a lot of the work is just getting the graph right. And then what has happened is the solve phase, which is where most of the actual work happens, where the typing logic is, has been a lot simpler than it was in Pyre, for example, which kind of did all of these at the same time. That's really all I had. I can open it up for questions, but you can learn more again at pyrefly.org. And if you really want to get into a lot more discussions, we'll have an open space tomorrow in room 321 from 4 to 5 p.m.
Yeah, it looks like I'm asking the same questions to all everyone. I've just and we actually had this in the chat. I was curious because this Pyre was internal tool, right? So mostly the goal for Meta was to use it internally. You open sourcing it now, right? And you starting to do like you're promoting it basically now. So is the plan to make it a tool for the community, or you just just trying out to make it kind of just public, but it is still mostly the tool for like you're focusing on your own use cases. So kind of what is the use case?
So I think there's two sides to that question. The first is, what about Pyre? Pyre is an open source tool. It was intended to hopefully be useful for the community, but we just kind of made it available. With Pyrefly, we really want to make it useful for the whole community. And this is... there are a lot of reasons for that. One is that actually the use cases are converging more. We have more people working with third-party libraries in partner teams internally. So we actually want to make sure the tools are seamless on GitHub. We want to make sure it works great with the third-party ecosystem. We also are hoping to just make the typing experience better in general. I mean, we're very excited about TY as well, because what we want to see, we believe that types make the Python experience better. We believe that a lot of the challenge of making that happen is really delivering the right kind of experience for the third-party ecosystem package maintainers to feel like they can adopt types, they can maintain it, and that their users get the value out of it. And really, that means all these tools are great. We wanted to do our part to bring a tool out that would make this kind of thing more possible for the whole community. And we're very committed to making sure that we're able to respond to pull requests and that we're keeping track of GitHub issues and taking them as seriously as we take any issues reported internally.
Hi, thanks for doing this first. I'm pretty excited to use it. Unhappy MyPy user at the moment. Speaking of which, MyPy stubs are pretty bad, especially with like modern packages, and it just not up to date. What's the equivalent solution for Pyrefly?
So I will say I don't think any type checker in the near term is getting away from stubs per se. At the moment, that is the source of type information. It's the only source of type information if you're looking at C extensions, and they're heavily used in some parts of the ecosystem because they have to be for performance. So I think what I want to actually talk about is that we recognize stubs as a problem. And there's actually in the discourse that I posted in the welcome slide, there's a post about an open space to talk about some efforts to improve typing. We've been working with QuantSite on this. It's not tightly connected to Pyrefly per se. It's more that we're trying to work with the third-party ecosystem to see if we can make stubs better across the board. But that's a less technical problem. It is a technical problem, but it's also a people problem, and making sure people have the right resources, especially package maintainers are frequently unpaid volunteers, so when you ask them to do a lot of work, it can be hard on them. That is at 3 p.m. tomorrow in 3:15.
So earlier you mentioned Buck integration as like a core part of this project, and I assume if I have a code base with Buck, like this is just great. If I don't use Buck, what does it look like?
If you don't use Buck, it should work pretty well out of the box. Really what we've done, I'll be honest, Pyrite has made a lot of progress on the problem of like, given a variety of ways that people could be running their project, what are some good defaults of how you would navigate the directory structure, how you would find the virtual environment. We are trying to do that. If we do find the virtual environment and things aren't configured enough, we'll run a little tiny Python snippet to try and figure out what's on the path, that sort of thing. So we took a lot of inspiration from the work that the Microsoft team has done already on how to best support the variety of use cases. And yeah, we are definitely, that's not second class. We have a lot of code bases that are not Buck code bases that we care about internally, as well as trying to make the best open source tools we can.
You said that one of your aims was to service other static analysis tools downstream. Does that mean I can get something kind of akin to an AST, but with types included? Is that the kind of end goal of that, or am I misunderstanding?
Yes, that at least. Some tools are going to need more than that, which is a part of why we thought we probably needed to make sure we could build the right APIs. In particular, we know PISA is going to probably need the ability to actually ask about subtyping relationships, which goes a little beyond just a typed AST. But yes, at least we want something equivalent to typed AST, whether it is exactly a typed AST or some other data structure.
Thank you.
Carl?
I mean, since you went into implementation stuff, I'm going to take it as an opportunity to ask about implementation stuff. I'm just curious on the binding. Can you go back to the binding slide that you showed? So I thought it was cool that you consider a narrowing constraint, like the if is instance x int, right, to be a new binding of x, is what I understood, right? So if you're evaluating the type of x from the point of view of the end of this scope, does that mean, like, are you able, at the end of the if-else, are you able to simplify that back to just the original binding on line 1, or do you end up having to, like, evaluate 2 bindings and the union of them where really the constraints just cancel out? Do you understand what I'm saying?
I see what you're saying. I actually am not 100% sure that...
We essentially have a scope, so we don't even union them or even simplify the union. We just throw away those 2 bindings when we get to the point they're no longer in scope. So it's kind of like a nested scope if Python had scopes.
And now Neil can potentially keep a mic in case there are any things I'm not qualified to answer.
So with these back-to-back talks about open source, Rust-based Python type checkers, is there any plans to like reuse, share code, solve similar problems in similar ways?
There are no concrete plans at the moment. We are already sharing the parser, which means we're actually sharing the AST, which may or may not mean that we're able to make compatible interfaces for things like how you would get a basic typed AST. But the type representations internally are, of course, not the same. So I think there are limits to how far that will be able to go, depending on the use case. Very good. Oh, well, one more, I guess.
I got asked earlier, so I ask it here too. Is this something that you plan to like replace monkey type, or is that something that already exists where you can enrich types onto the code? I mean, it could be part of the Gleam integration or whatnot, no? But
we would like to get as much type inference as we can. We did work on some tools many years ago with Pyre to try and get type inference. It was pretty limited how far we could get. I wouldn't say replacing monkey type is a goal. Monkey type is a runtime tool that's able to get a different kind of information than a static analysis tool is able to get. But I think we and a number of other parties are interested in various ways of finding types and being able to add them to code. I don't think we know the future of exactly which features will wind up in Pyrefly. We do have the feature where you can click on an inlay type hint and add it, which is probably the most useful for return types where we're able to infer them.
Is that part of the LSP integration only, or you can also do it from the CLI?
Currently, it's LSP only. We probably will be able to write a tool that modifies code. I don't know how soon that would happen.
Thank you.
Very good. I think we're pretty much at time, so I will end it, especially since there's no one with their hand up. And thank you. And I will invite Gia and Amritha up.
Hello, everyone. I'm Amritha. I'm from Instagram, Trust and Safety.
I'm Gia from the Pyrefly team. I'm Gia from the Pyrefly team.
And we're here to talk about preventing unwanted mutations with ImmutableRef. We'll speak about the need for immutability, though I think Bruce, even in his first talk, said immutability is awesome for safety, so always let's go for it. And maybe that's all I should talk about, and not show you all the code examples. And then we'll touch on implementation details and semantics, and then finally, we'll briefly talk about some of our adoption experience. This is a disclaimer. We are calling this as ImmutableRef for the purpose of this talk. In Pyre 1, the prototype, it's implemented as Pyre read-only. It started out as read-only, and then there was a naming clash. We think ImmutableRef is a more appropriate name, and so that's what we will refer to it as. So there are several examples, and we'll walk through a few of them. So let's start with this one. It is very common to have global singletons that we initialize once and ideally don't want to mutate later. In this example, we use a global singleton to store tool-specific configuration or customizations. You have the customizations object, you have a get customization API, and then you have an initialization API, which allows a one-time initialization. Yes?
Can you go full screen and make it a little bigger?
Where is the... Okay. Okay, back to globals and singletons. So so it is very common to have global singletons. We initialize them once, and this is the code example. So a typical usage would involve initializing the tool once, as you can see here in the bootstrap function, and then you use it multiple times with the same configuration. Within the tool library, or really anywhere during its usage, it's possible that we have a case where somebody fetches the singleton and then unintentionally mutates. This is because the developer likely doesn't realize that it was designed to be immutable. So if you were to use ImmutableRef and you marked the get customization API to return an ImmutableRef, you would have a typing error, and you can prevent such cases. Another example, and this was actually, I think I mentioned that I'm from Instagram Trust and Safety, was sensitive data processors. At Meta, we use ImmutableRef for this use case. Our use cases are much more convoluted, so this is a more relatable example, hopefully, for everyone. Here we have a function that is attempting to authenticate a user in a Django setting, say, with auth tokens. In our example, we use JSON web tokens to decode the token and determine the user ID. Once we get the user ID, we sanitize the token from the request to ensure we don't accidentally use it elsewhere or if it gets logged or anything like that. And finally, we return the user ID. Over time, code changes, and it's possible that we end up mutating the input argument. In this case, that is metadata, which is a dictionary, and we are stuffing the sensitive token data into it. This makes it hard to predict how exactly the sensitive token data will be used. For example, it's possible that the caller of the authenticate function could end up logging the metadata and unintentionally saving access tokens. To prevent such scenarios, we could mark the input param, in this case metadata, as an immutable ref. Now we'd get a typing error if we try to modify the data. In our code base, we something that I skipped is that we have special markers to annotate functions that deal with sensitive data. So we have requirements on top of this where we look at any function that has been marked with the special sensitive data processor marker, and we make sure that all of their input params are marked as immutable. This essentially helps us contain sensitive data within these functions, and it provides a lot of protection for us. Yet another example is concurrency. We could have two tasks both working on the same object. In this case, we have two different validation functions. And if both of them pass, as in if we validate the user's age and their karma score, we mark the user as verified. The user age validation is rather straightforward. We check that the user's age is above a minimum threshold, and then we say it's valid. However, for validating user karma, we do a lot of complex compute. So it makes sense for us to take a shortcut and say if the user is already verified, it's likely that their karma score is above a min score. However, this means that if we accidentally changed anything in user age and we marked the user as verified, we could run into race conditions and lead to inconsistent results. If both the validate functions, however, marked their input parameters as ImmutableRef, we could avoid such errors. There is a whole suite of applications that we could talk about. The main thing I think we want to touch on is that this feature provides an immutable reference. So there are instances in which you can actually mutate. So we could extend some of the examples we already saw for concurrent tasks to multi-threading, which will become more common with the GIL going away. Python today has getters and setters, but there is no actual guarantee that a get API does not mutate itself or the self object. There's also a need for an intermediate solution for data classes. You have the regular data class where you can do whatever you want and go crazy. And then you have frozen data classes, which are a bit too rigid. And with ImmutableRef, you can have certain blessed methods that allow you to mutate attributes without actually letting anything crazy happen. With this, I will hand over to Gia, who will talk about the implementation details and semantics of how this works.
So Pyre1 has implemented a prototype of this ImmutableRef idea. And this section, I'll provide an overview of the implementation. Let's start by looking at the new syntax required for this feature. We introduced an additional marker generic class called ImmutableRef, or PyRead-only if you're trying this in Pyre1. This marker class doesn't do anything at runtime, but we teach the type checker to recognize it so that when it appears at the outermost wrapper type of any functions, of any parameters or any returns of a function, we do something special. Here are some of the examples on the slide. In particular, the self parameter of any method can be annotated with ImmutableRef as well. We'll talk about what this means in a few slides later. Here, I just want to point out that it is by design that self parameter does not require any special casing treatment from any normal parameters. It turns out that allowing a special marker on parameters and the return type is all the syntax we need to get a very minimal setup for the system going. With all the syntactical setup, we can now start changing the type checker and implementing the ImmutableRef semantics. To get the very basic minimal viable prototype working, we implemented 4 basic typing rules of this in Pyre1. The first 3 rules are essential. The last one is not strictly necessary, but it is easy to do, and it is also a usability improvement, so I included it here as well. I'm going to walk you through these rules now, and trust me, although I've given them very fancy names, under the hood, they are obvious behaviors and should be relatively easy to follow. The first rule, I called it immutability, which basically say that if something is marked as ImmutableRef, then all writes to the attribute of the referenced object is banned. On the screen, you can see an example. We have a class foo with an attribute named x, and in the function, if we take an ImmutableRef of foo, then we won't be able to write to that particular attribute, foo.x. Here is another example. We return an immutable ref from the callee, and we get the same restriction on the attribute right on the caller side. This rule should be pretty uncontroversial. Not allowing to mutate the attribute from ImmutableRef is the very definition of immutability and the very motivation why we want this feature to exist. The second rule, I call it deepness. This rule basically controls how immutable refness is propagated in the program. It says that if an object is immutable ref, then any attribute read from it also hands back an immutable ref. Here is an example. Foo is a class with an attribute named bar. And in the function test, we take an immutable ref of foo, then reads the attribute bar from it. We can see here that the type of foo.bar in the function is immutable ref, even if bar is not marked as immutable ref by itself on the class definition of foo. And we can't mutate that bar attribute within the test function because of the immutability rule mentioned before. This rule should also be intuitive. If it doesn't hold, that means we could grab a mutable reference to bar from an immutable reference of foo, which implies we'll be able to mutate part of the foo, which breaks the immutability guarantee in the first place. The third rule dictates how immutable ref objects interact with other with their non-immutable ref counterparts. It basically says that if I have a mutable ref of type T, I can turn it into an immutable ref of the same type. But this conversion is unidirectional. If something is already immutable ref, I can't freely convert it back. Here is an example. I have two functions, one that requires immutable ref parameters, and the other one requires immutable ref parameter. On the caller side, if my foo is mutable ref, then I can pass it down to both functions. But if my foo is immutable ref, I can only pass it to the one that requires immutable ref parameter. I can't pass it to the one that expects mutable ref of foo. This rule basically states a similar principle as the previous rule. The type system should not allow getting a mutable reference out of an immutable reference. We don't allow it for attribute access on the immutable ref in the previous rule, and we shouldn't allow it for the immutable ref itself, which is what this rule dictates. This is an implicit consequence of this rule. Recall that earlier I mentioned that self-argument method can also be annotated with immutable ref. According to this subtyping rule, we cannot pass an immutable ref to a function that takes mutable ref as argument. And therefore, if my self-argument is mutable on the method, my method simply cannot be invoked from objects with immutable ref type. This is exactly the same example I have in the previous slide, except that I've changed the two callees from functions to methods, and I've applied the immutable ref on their self parameter instead of their regular parameter. The caller side behavior should be exactly the same as before. If my foo is mutable, I can invoke both of these methods, but if my foo is immutable, I can only invoke the one that has immutable ref as self. Another consequence of the subtyping rule is that if we override a method that takes an immutable ref parameter, we cannot simply cast away that immutable refness on the parameter in the overriding method. If base class method takes an immutable ref foo, then overriding method in the subclass that takes mutable ref foo would be flagged by the type checker through the inconsistent override check, as implied by the subtyping relation. This kind of check is not added or invented for the immutable ref feature. It's something that's already there in most of the type checkers, and it plays really well with this particular rule. The final rule here is technically speaking not essential to get a bare-bone minimal bare-bone immutable ref feature working, but it is a trivial extension and it improves usability of the system a little bit. It says that if you already have two types, T1 and T2, and if T1 is a subtype of T2, then wrapping those types with immutable ref would preserve that subtyping relation. In type checking jargon, we're saying that immutable ref is covariant. On the slide, there's an example. If my callee takes an argument of immutable ref of sequence of int, then it should be OK to pass an immutable ref of list of int to it. Here is a small diagram illustrating the subtyping relation among these four types, T1, T2, immutable ref T1, and immutable ref of T2. This rule basically offers another way we could obtain an object of type ImmutableRef T2 on the upper right corner. With the previous rules, we can only obtain ImmutableRef T2 from MutableRef T2 on the upper left corner. This rule allows us to obtain ImmutableRef T2 from another ImmutableRef of T1 on the lower right corner, and this in turn lets the type checker accept more programs, and therefore it is a usability improvement. That concludes my summary of what it takes to support ImmutableRef feature in Pyre 1. It's definitely not a trivial extension to the type system, but I also feel like this is not as big of a change as I initially anticipated. Though I do want to point out, again, that our ImmutableRef implementation in Pyre 1 is just a prototype. We tried to capture the core essence of the feature with those 4 rules, but if we were to fully integrate the feature into the Python type system, there will be more things to consider, especially when ImmutableRef starts to interact with many of the other pre-existing type checking features. For example, do we want to allow ImmutableRef to appear in more places than just the top-level parameter and return annotation? Should we allow it for attribute annotation, or base classes, or type? If so, do we need to adjust other places in the type checker to cope with these changes? Another implication of this feature is that the top type of the type system now becomes ImmutableRef of object instead of just object. And are there any places within the type checker where we're hard-baking the assumption that object is always the top type, and how do we want to adjust that? Another, how would container variance be affected by this feature? Should we allow something like this, where the invariant list type, when applied on ImmutableRef, becomes covariant? And how would ImmutableRef play with type variable variance inference for user-defined generic classes? I believe we're having a talk on this. I'm looking forward to it. Should we change our type inference algorithm to infer ImmutableRef types more often? Should we improve the ergonomics of this feature by inferring ImmutableRef on self-argument, as opposed to always requiring the user to declare them explicitly? This is a non-exhaustive list containing questions that has not been answered by our prototype, but probably need to be addressed or considered if the feature is to be productionized and added to the typing spec. Our experience also indicates that very often, methods needs to be defined in such a way that if they are invoked on ImmutableRef arguments, if they are invoked on immutable arguments or immutable self, we get ImmutableRef return. But if invoked on MutableRef argument or MutableRef self, we get MutableRef return. On the screen, you can see an example. Today, this thing is only achievable with overloads, which does make it very awkward and very cumbersome to define. Having some way of getting this kind of polymorphism without involving heavy overload syntaxes could also be a great improvement in usability. With that, I'll now hand over back to Amritha to talk about her experience in adopting the ImmutableRef feature.
Okay, so we have actually adopted ImmutableRef in Instagram's code base, and I'll talk a bit about that. So adopting ImmutableRef is a bit involved, and we can look at this example. You have a class A, which has an attribute vals, which is a list of int. You have a function getA. You have foo, which calls getA, and bar, which calls baz, and baz, which calls other func and does a few things. If we just mark the return type of getA as ImmutableRef, we'd see a Pyre error in bar. Notice that we can skip making any changes to foo, since we didn't see any effects there. If we fix the error in bar, we'd see an error in baz, even though we only pass the attribute vals. So fixing all Pyre errors would require us to fully propagate, or fixing all type errors would require us to fully propagate the ImmutableRef everywhere in the call graph. So with that knowledge, let me try to summarize a bit of our adoption experience. Our code bases have very complex call graphs, and we are not starting with just introducing ImmutableRef into new code. We're trying to retrofit ImmutableRef into our existing code. So if an object is marked as ImmutableRef and is threaded across our complex call graph, we need to propagate the annotation across all the functions. This is applicable, as we saw in the example, even if we only pass an attribute of the object because of the deepness constraint that Gia just spoke about. To overcome this, we built a script which uses libcst to build automated code transforms that would automatically propagate the ImmutableRef annotation. Ideally, this would leave us with a bunch of type errors that are likely true mutations for us to fix. One thing that was actually helpful was that we implemented this as a typing-only change. We did go back and forth initially as we were deciding whether this should be on the runtime or typing change, but especially for us to roll out at scale, it was really useful because we could make a bunch of mistakes, rely on automation to roll this out without blowing things up in the site. We also see a lot of type errors from standard library APIs. So I was saying that ideally, if the script worked beautifully, we would only see true mutations that are bad things that we want to go fix. But we also get into cases where, for example, you have list.get or dict.get, and we don't think those are doing mutations. But we've been overcoming these by forking the typeshit stubs. And this has been difficult to be exhaustive about, and also brings about maintenance overhead due to the forking. And because ImmutableRef needs to be propagated everywhere, it would be a better adoption experience if the type checker didn't insist on propagating this for immutable types like int. I think one of sometimes there have been cases where you, at least in my experience, try to add an ImmutableRef annotation to one function and it has gone 300 levels deep. And most of this crazy depth came from ints, which at least are immutable apart from the risk with subclassing. And that would bring a huge quality of life improvement in terms of adoption. So it's a very high-level summary, but we're both here to answer more questions if folks want to talk about this.
Okay, I'm super confused here. Did you mention final and I just missed it? Or is it obvious that this is different than final with the capital F final?
Final is not deep. An intuition for final is that the reference cannot be rebind. And where the ImmutableRef says that you cannot mutate the underlying object from this reference. It's talking about two different levels.
Okay. Yeah, I needed to see that in the front. Thanks.
So are you going to allow typing.cast to cast away immutability?
Yes. So this will be, if we're doing some serious guarantees, then we'll have to look for those as well.
So as you were talking about adoption potential difficulty, I kind of thought back to the gradual guarantee of like any types, sort of as an example, or object being the base type too of like the full language. Like if object, you sort of took the approach that if it's not an immutable ref, therefore it is mutable. But you could have also said like it's uncommitted or it's unknown or it's somehow more open. I haven't thought about the full implications of this, but perhaps you've spent more time. I thought it might help with adoption, but it probably has other consequences that I can't trace.
Can I be more specific?
Sorry, I was encouraged by some nods.
Sorry.
So we actually didn't ask for that, but I think in retrospect, it would have been useful at least to break down the difference between the ones where we know are true mutations versus the ones that we don't know yet. We didn't do it, but thinking back, I think it would be useful.
Yeah, I had a question because you showed the example with dict, and you also used lists, and obviously, as you said, there's subtyping, right? So anything can be mutable in, but there's already mapping, there's already sequence, right? So for the cases where you're just using the collections, you already it's not deep. I understand there's a difference, right? So you're going deep, right? For the mapping, you actually prohibiting the mutating the internal elements. But in real life, that's the question from adoption. Did you consider doing like sequence mapping first,
or you just most of your use cases are custom classes, so it's not that valuable as doing all the work with like a new concept like ImmutableRef?
I'll say sequence, and those are like very specific examples. We wanted more general solutions where like for any object we don't want the object to be mutated anywhere downstream. That was a bit of our motivation, which we wouldn't get just by like going to specific examples and marking them as sequence or mapping instead of list or dict.
This is going to be a really broad scope question, but a trend in the last 20 years plus has been in programming languages has been to make immutability the default, and you spend syntax to buy mutability. Obviously, we can't do that in Python, and so I wonder if there's a point at which it becomes valuable to have a programming language with what we might call a modern type system that compiles to Python bytecode for your Python programs to import. I don't know if you have any thoughts on that, or if you think that might be a valuable space.
You could call it mypyc. Or Python 4. Okay.
So with your types, so with the types, you've got immutable ref, and if you were to nest those, so like immutable ref of list of immutable ref of something, the inner immutable ref, do you eliminate that because it's equivalent, right? Because the immutable ref of immutable ref of list of immutable ref of object is identical to immutable ref of list of object.
I think it's functionally yes, but
would it subtype, like if you pass it? Or?
For subtyping, I don't think they are identical with respect to subtyping, right?
But whenever you look inside it, right, you're going to have to apply the immutable ref internally, so it passes through the whole type thing, or I guess.
Well, I mean, first of all, like to do that kind of stuff, we first need to allow like immutable ref of list to be covariant. That thing we haven't implemented, so okay. I wouldn't. There will be more to explore on that kind of trickiness, but yeah. Other than that, if things get nested, I think from my own experience, everything else just falls through. But yeah, there might be edge cases I haven't thought about.
So in C++, experience with const suggests that a lot of const casts come about because of parametricity, of methods where if the thing that you pass it is immutable, then the result you get is immutable. And if it is mutable, then the thing you get is mutable. That seems like, in the context of the Python type system, that seems like it would lead to a lot of overloads for libraries that are very general. Have you considered some way to address mutability parametricity otherwise?
That is one of the items that I put in the end. I don't think we have a perfect answer for that question. Some of the things that we might choose to do, for example, inference, like if your function doesn't mutate anything, then we give you both versions. That could be a way to do it, but we can also consider like special syntax to mark the component, that kind of parametricity. But yeah, if we're under the constraint that syntax is fixed, then it's hard.
Hi, here. So I think you mentioned, but I didn't quite catch it. Whenever you have an immutable ref of something like a custom class, and the custom class has a method, whenever I call on the method, does self implicitly become immutable reference? Okay. So if I have a class which wasn't designed to be immutable, but in this scope I want it to be immutable, I can have a guarantee that it's whatever the methods do, it would be.
Yeah, if the methods only have reference to that thing with immutable ref, then we have the guarantee that it can't mutate it.
Even if it is self, right?
Yeah, even if it's self.
And it is implicit?
Implicit?
So if I have immutable ref and that's variable a, and I call a dot spam. Self inside spam is okay. Thank you.
Wait, in practice, doesn't it not let you call the function?
Yes, it should be.
I think what happens in practice is if you have foo and if you have a, let's say you have a method called update, which takes self and it does something. If you had an instance x, which was an immutable reference to it, if you try to call update, it would just give you an error because update has not been, does not annotate self as an immutable ref. So we're saying that self, because update, I mean, here in this case, the name is very obvious that it is doing an update, and you do have an immutable ref of foo, and so you should not be able to call the update method. There might be another method which is just doing like, I don't know, get something. If you don't go and annotate self as immutable ref in the get something, you'll also get a type error if you try to call the get something, but you can go and like change the attribution, change the annotation on self for that get something API, and then you would not have errors. Essentially, that's one of the main things that this provides is not just like attribute assignment, but you cannot call any methods also on the object that could internally be mutating things.
Okay, because like what my question was for like libraries, right, that are not thought with this in mind, and they might have some update and some get, which okay, thank you.
I'll add that one of the things that Ed mentioned is that it's really hard. Today you have, at least we've seen APIs which are called get something, so you would assume that they're not doing any mutations, but internally the get APIs are changing things. Like I could come up with a convoluted example that it has a counter that increments the number of times you called get or something like that, right? And today we don't have those guarantees that you're not making any like side effects when you call the method. So you have to actually go annotate every instance method that you're claiming doesn't actually do any mutations with marking self as immutable ref.
We need to move on to the next talk. So maybe you need to have an open space about immutable ref. So Martin?
I'm Martin. I work for Google, as I mentioned earlier, when we had to press Shift Command F. I'll be talking. Okay, so I have this habit of walking around a little bit, and then I move away from the mic. If I do and you can't hear me, can you just like wave or something, kind of like to push me back? Yeah, I work for Google, and I work on our internal language server for Python. So we have another one. It's not yet open source. It hopefully will be soon. And as you all know, language servers have like to do two kind of different things. First of all, they're query handlers that answer questions like, what's the type of this identifier, or give me all the completions at this point. And then there are like the task of producing all the diagnostics for a file, basically finding all the type errors. And particularly for the blue box, you want to have very on-demand computation, right? To compute the completions at a specific point, you don't want to check your whole code base, right? So everything has to be on demand, and you also want it to be incremental, to be snappy. So what you end up is you have a semantic analyzer that is on demand, but you don't know what you need before, and you don't know if you will ever need it again. So you also have to cache everything we do. This is kind of like the setting in which we're operating. And I want to apply this to like one specific problem, which is variance inference. And before we go to variance inference, let's do a little warm-up to recall what variance was. So first of all, I guess you all agree that snakes are animals. So we write this as like snake is a subtype of animal. And then there's the absence of variance is called invariance, which gives us that a list of snakes and a list of animals, those two types are incomparable, right? Like if you have a list of animals, you can't use it like a list of snakes because you would get an animal, right, instead of a snake. But it's also the other way around, it doesn't work, because if you have a list of snakes and use it like a list of animals, you can put a dog among your snakes, and that might not be cool, right? So this is invariance. Those two types don't subtype in either direction. Then we have covariance. If our sequence or our list happens to be immutable, kind of like the subtyping between snake and animal propagates through sequence. So if you have a sequence of snakes, which is immutable, you can use it as a sequence of animals because you can only ever read. You can never write. And then there's the opposite thing, which you get for callables, which is called contravariance. So the key thing is in argument position, the subtyping relationship kind of changes, right? Like snakes are animals, but callables that expect an animal are a subtype of callables that expect a snake, right? If your function, I don't know, can determine whatever property of an animal, it can specifically also do it for snakes, right? So this is a refresher or a warm-up on variance. And why is variance important? Because there was this PEP 695 that got implemented for Python 3.12, which introduced a new syntax for generics. So with the old syntax, if you wanted to declare a cage type for your animals, you had to do like all the ceremony where you say like X as a type var, and then you had to like say your type, your class is generic. And then because our cages are immutable, we also want them to be covariant. So we also had to explicitly say that. And then in 3.12, we got this new syntax where basically all this blue ceremony got replaced by just like we say cages generic with a type parameter called X, and it has a bound of animal. And I know that usually people call type parameters T. I use X because I also need like a meta variable for types, and I'll use T for that. Cool. So the question is like, how do we tell Python, the type checker, that cage should be covariant, right? There's no way in the syntax to do this. And the answer that PEP 695 has decided to give is we infer the variance. So yeah, we basically do static analysis on your class and determine what's the safest variance we can give to X or to cage. And one caveat, I'll only be talking about generic classes that take a single type argument, but everything I say applies to multiple as well, right? But just like to keep things simple and easier to follow. All right, so how does the algorithm, what does it look like that is proposed by PEP 695? Before we dive into that, here's the abstract definition of covariant and contravariant. So if we have a generic class, it is covariant if a subtyping relationship between its type arguments S and T propagates through the class, right? Kind of like if S is a subtype of T, then C of S is a subtype of C of T. That is covariant. And contravariant is where the subtyping relationship flips. If S is a subtype of T, then C of T is a subtype of C of S. Cool. And this is the formal definition. And in contrast to what PEP 695 suggests, like those two properties are independent, right? You can be one or the other, or you can be both. So kind of like we just treat them as two independent properties. They're like not opposed to each other or anything like that, at least in theory. Like the Python implementation has a different opinion. Cool. So what does the algorithm do? Basically, it reduces the problem of inferring variance to subtyping, and it uses some sort of parametricity and the fact that X is a subtype of object because everything is a subtype of object as of now. Cool. So basically, the algorithm says that C is covariant. If structurally C of X is a subtype of C of object. So basically, this is to be interpreted as if we can provide a proof that C of X is a subtype of C of object structurally, then that proof basically translates to all types, right? Instead of X, you could use S, and instead of object, we could use T. And what do I mean by structurally a subtype? Basically, we treat, in our example, we treat cage as if it was a protocol, right? Kind of like, so we look at the fields and methods and do subtyping on those. So we do structural subtyping, and we have to strip the constructor as well. Cool. Yeah, and when you see that, or at least when I saw that, one of the immediate questions was, what happens if we have recursive classes or even mutually recursive classes? And to see what happens, let's just play it through. So here's some code, and now we'll be a type checker for a few minutes. So we have a generic class C with two methods f and g. And then we have another class D with a method h. And one of the methods of C returns a D, and one of the methods of D returns a C, so they're mutually recursive. And then we have a function called cast that takes a C of bool and returns a C of int, and it basically should just like pass it through. So when a type checker has to check this, if this is valid, right, it basically has to check if C of bool is a subtype of C of int. Right? And one way to do this, I'm not saying every type checker does it like this, would be first we check the arguments. Okay, bool is a subtype of int. Next, we need to check if C is covariant. Because if C was covariant, then C of bool would be a subtype of C of int. Right? That's what covariance means. Cool. So this unfolds into we check if we have if C of x is a structural subtype of C of object. If it is, we need to like do, or kind of like what, not if it is. To check this, we need to do like the structural checks. So we need to basically check if the type, the signature of f of x is a subtype of the signature of f when we use object instead of x. Right? So, and to do this, we basically come to a point where we need to determine if d of x is a subtype of d of object. And to do this, we check is x a subtype of object, which it is. So we go down to checking is D covariant, right? If it is, then again d of x is a subtype of d of object, right? And then if we like unfold what does it mean for the covariance check for D, we basically get to a point where we need to check is C covariant, right? Which is actually what we're trying to determine. And subtyping in this context is defined co-inductively. And, my slides got slightly rearranged, very sad. So at this point, we detect a loop, right? We need to determine if C is covariant, we need to determine if C is covariant. And the essence of a co-induction is basically whenever that happens, the answer is yes. Right? Kind of like if you run into recursion, you just return true in this example. And this thing then bubbles up, right? This means C is covariant, which in turn means that D is covariant. And then we basically get to the point where we need to check if this G thing is covariant, right? So we have to check because this is an argument position, we need to check as object a subtype of X, which is false, which means C is not covariant, right? Because we just found that this violates the covariance assumption. So that means, and we can see that if C is not covariant, then D is also not covariant, which means here for this query is D covariant. We got the answer true, which is actually false, which means we can't put that intermediate result into the cache. So all those intermediate computations we've done here are garbage, right? And that is kind of sad. So we've wasted a computation. And yeah, because C is not covariant, basically this check fails, right? And we get a type error. I hope all our type errors look better than this. Anyhow, but worst case, what can happen is if we have enough mutually recursive classes, checking covariance for all of them becomes quadratic, and that's the sort of thing you don't want to have in your LSP or in your type checker. So how do we get rid of this? Let me take a sip of water quickly. So what I'll do for the rest of this talk is I'll propose a different algorithm that will turn out to have linear runtime. The input to our algorithm is a bunch of classes, C1 to Cn, and we assume like they're close under dependency. So whatever C, any of the Ci mentions, must be among those classes. And the first step will be to traverse all the signatures of those classes and emit a bunch of Boolean equations. In step 2, we solve the system of Boolean of equations we get, and then in the end, we look at some specific variables and they tell us what the variances will be. And the result of this algorithm is the optimal variances for the classes. Optimal in the sense that what it returns is safe, but it also returns as many things are covariant or contravariant as possible, right? Kind of like making everything invariant, like neither covariant nor contravariant, is safe, but super inconvenient, right? So we want to make as much co or contravariant as possible. And regarding the runtime complexity, to generate all the questions, we basically just walk over all the signatures and output questions. That takes linear time, or time linear in the input size. And then we need to solve all those equations, and that takes time linear in the size of the equations, which must be linear in the size of the input, because it has only taken linear time to generate the equations. Cool, so before we can phrase this algorithm, we need to do like one slide generalization of the notion of variance. So far, we've only talked about the variance of classes, and now we'll be talking about the variance of types. So we say a type T is covariant in a type variable X if whenever U is a subtype of V, then replacing X in T with U yields a subtype of replacing X in T with V. Right? Does that make sense? Cool. Okay, and contravariance is again the other way around. And a few quick observations. First of all, if X does not appear in T, then T is co and contravariant in X, right? Because replacing doesn't change anything. If C is a generic class, then if C is covariant, then C of X is covariant in X. That's also relatively obvious, and contravariance the same. And the type, like if we regard the type variable X as a type, which you can do, then it's covariant in X, but it's not contravariant in X. Right? So those are like some basic building blocks. And then we use this generalized notion of variance to come back to our example. So those are the two classes C and D from before. And before I go like into any more abstract presentation, I'll just like run through the algorithm on this example again. And we have a bunch of Boolean variables because we want to generate Boolean equations. So for instance, we have C plus, which stands for C is covariant, and C minus, which stands for C is contravariant, and similarly F plus X, which stands for the signature of this F is covariant in X, and similar F minus X for contravariance, and so on. And then if we look through this, the first few equations we get is for C to be covariant, F needs to be covariant in X, and G needs to be covariant in X. This is basically the normal check we've done before. Then similarly for contravariance, then for F to be covariant in X, its return type has to be covariant in X, which means basically D has to be covariant, which is here. For G to be covariant in X, it has to be X has to be contravariant in X, right? Because this X appears in an argument position, we need it to be contravariant. And none has to be covariant in X, which is the case, and so on. So that's how we generate those questions. And then we have some basic facts, like X is covariant in X, but not contravariant, and none is co and contravariant in X. Right? This is how we generate the system of Boolean equations. And now, how do we solve them? We basically propagate all the truths and falses. We kind of like bubble them up. So we have a bunch of variables that we already know are true or false, and then we push them through. So for instance, we know, my finger, on my MacBook I can just touch it and nothing happens, but here it's different. So we know this x is false, and that means like this whole thing must be false, right? Because false and something is false. Whereas here we know x and n are both true, so g must be true, right? And then we continue propagating. Up here we know g plus x is false, so c plus must be false, which means c is not covariant, as we've seen earlier. And here we know g minus x is true, which means we have to simplify this equation. That's an important step, kind of like we want to reduce, like simplify the equation system where we walk through it, right? And like we can push it up all the way, and if we do this, we get to this point, and we arrive at a point where everything else is kind of like unspecified. And in this position, we can set just everything that is left over to true. This gives us the optimal variance that I mentioned earlier, right? So we compute like the greatest fixed point in the sense of the Knaster-Tarski theorem. Cool, so everything is true. And then in the end, we take those, like the assignments to those variables up here and read off the variances, right? So we can read off that C is contravariant but not covariant, and similarly D is contravariant but not covariant, right? Okay, cool. So now, what are the steps we actually did? So first, we generated equations for classes, and let's be like slightly more general here. We have a generic class with a base class, we have a final field, we have a mutable field, and we have some method. So for C to be covariant, in B has to be covariant in X. The type of the A field has to be covariant. B has to be co and contravariant in X. And this whole signature of F has to be covariant in X. And for the signature of F to be covariant in X, U has to be contravariant in X because it's an argument position again. Same for V, and W has to be covariant again, right? And we similarly kind of like, if we swap all the pluses and minuses, we get the right equations, which are for contravariance. And the intuition for fields is that basically a final field behaves like there's just a getter method, and a non-final field behaves like there is a getter and a setter method. This will like lead to exactly those two things. So this is how we generate equations for classes, and then how do we generate equations for types? I'll just walk through some examples. For instance, if we have a union type S or T is covariant in X if both S is covariant in X and T is covariant in X. Similarly with contravariance, for a tuple to be covariant in X, both components need to be covariant. And for like an for a homogeneous tuple to be covariant, it has to be covariant as well, right? This is one way how we generate equations, and then the other one is how do we generate equations for specializations of generic types or generic classes. And there's a theorem we can like prove in a very formal sense that if we have a generic class C and a type T and a type variable X, then the type C of T is, let's focus on the blue parts first, is covariant in X if one of four conditions is met. If C is covariant and T is covariant in X, then the combination is covariant, kind of like covariant plus covariant makes covariant. If C is contravariant and T is contravariant, then again we get something covariant, like contra is co. It could also be that C is covariant and contravariant at the same time. Then the whole thing is a covariant. I think like in Python it basically never happens, but it's like theoretically possible. And also if T is co and contravariant in X, then the whole thing is covariant. And this actually happens, right? Like if you instantiate T with int, for instance, right, like C and C of int, and then int is covariant in X, right? So, and contravariant. So C of int is always covariant in X. There's just no X. Right. Okay, and then you can like, if you swap out some co and contravariants, you get the right theorem. And these equations, or like this theorem, can be perfectly put into equations as well, right? C is covariant in in X if one of like those 4 things is met. So everything translates perfectly into the logic we are looking at. Cool. So this means we can come back to our algorithm and fill in like some tiny gaps. So this is the algorithm as we saw it before. In step 1, we can actually be a little bit more incremental. If we've already inferred the variance of Ci at some point earlier, then we can just like plug in true or false, right, for the variances. And just to reiterate what I said on how we solve the Boolean equation system, we propagate the constants and simplify as long as we can. Once we've exhausted all opportunities to do that, we set all the unconstrained variables to true. And this is sound and optimal. Optimal in the sense it gives like the most subtyping relationships. It's the most convenient for us as people who write Python. And what we get this way is called the greatest fixed point of the equation system, in the sense of the Knaster-Tarski theorem. And then in the end, we read the variances of the assignments to those special variables, C1 plus, C1 minus, and so on. Cool. So this is the whole algorithm. And there are a few open questions I have for this. First of all, is like, how can we like make this short circuit better, right? Kind of like right now, if we want to determine the variance, we basically have to like write down the whole equation system first and then solve it to get something. Maybe you want to do like more incrementally. As soon as you know the answer, kind of like leave the equation system in a half-solved state or like even a half-generated state. Kind of like sort of an online algorithm to do this. The second question is, can we actually use this approach to improve the incrementality and caching for subtyping? So if you have like a structural type system with recursive types, you basically run into the exact same problem, right? Where you have like, where your intermediate subtyping checks are bogus. So can we use the same idea here? I guess yes, but I haven't thought about it in detail. And last but not least, can we somehow like make the support for immutable structures better with our variance inference? For instance, if we look at this pair class, which is immutable, right? Like first and second are final fields, and then we have a method that basically gives like a non-destructive update function. So there's no reason for this class to not be covariant, but this inference algorithm described in the PEP, or what I just described as well, would infer this as invariant, which is somewhat sad because it could be covariant. So can we do better? Cool. And that's all I had. Thank you.
Thanks. Yeah, I think we do very similar things in Pyre 1, but I like your formulation here. I think this is much cleaner. I have a question to this algorithm, though. It seems like is it the assumption here is that before we infer variance, we know all the type signatures. All the type signatures have been laid out explicitly.
I think so, yeah.
So if have you thought about how do we do this if we have, for example, return type inference?
I see. I guess for return type inference, you kind of like wouldn't get problems. Do you need, like, you don't need to check actually types, right? Like subtyping is only relevant if you ever like need to check somewhere. Well, there's overload resolution where you might need to check to get the return type. No, I've not thought about this in detail yet. I've basically just like taken the PEP 6.5 algorithm at face value. Yeah. Yeah, one thing I haven't mentioned actually is like, it's actually, this algorithm is very stratified, right? Like the variance inference and the subtyping are not interleaved anymore. You first do one and then you use the result in the other. But yeah, I haven't thought about return type inference.
Yeah, so the previous generation of type vars where people explicitly specified covariance or contravariance, like would it be worth running this check over them and making sure that, for instance, type shared is consistent with respect to what it's manually specified?
That is a good question, right? So if we come back to the pair example, and if you write this in the old syntax, you can declare X as covariant, which gives you the behavior you want, right? But then the check, like the inference would say, no, it's not covariant, and kind of like this is the only way to actually override faulty invariances, right? Or like some that are too conservative. So I don't know. I guess it's like it's a good helper, and you might want to opt out in some cases where you know better. I guess it's a trade-off. Also, there's like maybe it behaves different for protocols, right? Because they kind of don't have an implementation. So you kind of like there could always be an if this was like just a protocol without the implementation for this one here, I think it's fair to say this must be invariant, right? Because like there's no implementation that can guarantee that it's not invariant, right? Because every implementation can do whatever it wants. So maybe the situation is different for protocols.
Protocols always have an explicit subtype relationship?
No, but like they could have a variance, right? You would want to know that, yeah.
If this were a protocol and you have implementation, then you're saying it would be in. I guess you couldn't know that it wasn't in there. I'm just curious if this were a protocol, so we didn't have implementations, then we couldn't say it wasn't invariant because, like you're saying, the implementation could do it. So it's sort of treating this case independently of the implementation.
Yeah.
Which is, okay.
Yeah, I mean, there could be like implementations that make it covariant, and there could be some that make it invariant, right? But you don't know. You have to cover all the cases, unfortunately.
I have a quick question. If something doesn't have like any variance restriction, so if it's like bivariant, do you just pick, or what do you do?
So we haven't implemented this yet, but like we would make it just bivariant, right? Like it's just like two independent things. As long as we don't have to like if you like actually try to instantiate a type var using co and contravariant, both true, it will tell you I don't do bivariance. But I mean, there's no reason for a type checker to not do this, right? So we would do this, yeah. Cool, thank you.
So yeah, I'm Rebecca. I work on Pyrefly at Meta, and I am also a member of the Python Typing Council. So I'm going to give some quick updates on what we've been up to. So first, what is the Typing Council? We're a fairly new group formed a couple years ago. We maintain a few key parts of the type system, specifically a formal specification, a test suite that contains some tests you can use to check whether type checkers are conformant to that spec, and also a user-facing reference. And then we also provide recommendations to the steering council for the Python language as a whole on typing-related Python enhancement proposals. The Typing Council has 5 members. Eric, Jella, and I have been on it since it was formed, and Carl and Jukka joined in the past year. And our official written communications you can find at the Typing Council GitHub repo. So what's been going on with the type system? In the past year, a big landmark, I guess, is that thanks to the hard work of Eric and Carl and many other contributors, the conformance test suite has been completed. So all sections of the typing spec that you sort of can test have tests. There have also been some major improvements to the spec itself. I'm going to highlight just one that I think is really cool, which is that we now have a type system concepts section. So if you're interested in gradual typing and like the theory behind the Python type system, I'd encourage you to give this section a read. It's very accessible. So where would you find this Great writing. The spec and the user reference both have a shiny new home at typing.python.org. And in the past year, finally, there's also been one typing PEP that was accepted. That was PEP 749 by Yella. So what's next? In the past year, only one typing PEP was accepted, but quite a few more have been drafted. So one thing we're hoping to do is, get a few more of these PEPs over the finish line and some more great ideas to our type system. I don't know if any of these authors are here today, but if you are, please submit your PEP for consideration by the Typing Council. One thing I do want to point out, because I think it's pretty neat, I have 7 PEPs listed on this slide. Every single one has different authors, which I think just goes to show that, Python typing, it's really a community effort. Most of the ideas to improve the type system, they don't come from the Typing Council, they come from you all. So moving on, another thing we want to work on is that the typing spec is still a work in progress. This was a slide that Eric shared at a typing meetup last July, listing what were at the time some of the main gaps in the spec. Since then, we've filled out a couple of these sections. As you can see, there is still a lot more work to do. So going back to the type system sort of belonging to everyone, we really would love all of y'all's help in filling out the spec. Next year, I hope I don't even need to give this update, just show a solid green slide. So if you do want to be involved in typing, where do you find us? All the interesting discussion happens in the typing category on Discourse. Again, the spec and the user reference are at typing.python.org. We'll take a peek at the source for the spec or at the conformance tests. They're in the Python typing repo. And again, you can find the Typing Council communications, the Typing Council repo. That's all I have. Thank you.
Q&A for the Typing Council? It was. At least the 3 of us who are here. Okay. Do we need to sit up front, or can we just sit where we are?
Hi, I was wondering, what is each of your favorite type and why?
Eddie! You took my answer, you know. Come on.
Well, you can be original twice.
We have a mic.
Yeah, we need one mic for the council. We'll have to run.
Any is my favorite type because it's what makes the Python type system interesting.
I guess I can't repeat any. So I'll just say the most commonly used type is just a class like int, str, my class. That's very useful, and that's kind of, we couldn't do anything without it really.
I guess my favorite class is protocol. I like structural subtyping. It's also in some ways my least favorite class.
So with async and now free threading, we're seeing a lot more concurrency in Python. And one thing I haven't seen is proposals for type annotations for concurrency properties, like lock guards or thread safety of methods, things like that. Is that on anyone's radar as a near-term extension?
I'm going to hazard no.
Yeah, it's not something I've seen a lot of discussion of. I mean, the Python type system as it is currently implemented by type checkers is fairly unsound when it comes to concurrency. I mean, the fact that we're willing to narrow types of mutable attributes that objects that could have references in another thread or something, and we just consider that a worthwhile trade-off because of the convenience of the code it allows us to write. So I think there's certainly going to be a lot to think about there with free threading, but I don't have answers right now.
Yeah, I don't really have any clear answers either. But even though the type system is kind of unsound by design, it doesn't mean that it's not useful. So even like we don't need to find all type prevent concurrency bugs, even something if we can help find like a significant class of them, that could still be quite worthwhile. And it would still align with the philosophy of kind of trying to be helpful while being like easy to use and kind of pragmatic.
I have a question. So we ran a survey over the summer which showed one of the top challenges with the type system was actually just documentation and onboarding and how to learn about it. One of the charters for the Typing Council was to improve documentation and think about this. Is this something on your mind now or a plan?
I agree that documentation is important, and I kind of spread out. There's like tool-specific documentation. There's some generic ones, but it's kind of, yeah, I think it's a bit messy, and I think we should probably invest more effort into this. So I think it's a good call out.
Yeah, I think mostly just there were a lot of things in the charter of the Typing Council, and you might notice that a few of us are busy trying to write type checkers. So there has been a lot of effort that's gone into improving the spec and the conformance suite, which in some ways feels like we have to know what the type system is before we can document it. So it feels like a sensible ordering. But obviously we aren't getting to the documentation very much, and all of your pull requests are welcome.
I guess sort of echoing that, I think if you ask all of us, we will all agree that documentation is important, and then you ask which volunteer has time to do it.
I had a question, and I'm sorry if I missed, but I think among those PEPs that he showed, right, there were no intersection. And I tried to follow the intersection discussion, like it was 2 years ago, and like it just bailed out. And I know that TY has it, but I just recently had to code for 3 weeks in TypeScript, and suddenly I realized that intersections are actually useful, right, for combining APIs, for example. I actually had a problem in my own project. So is it somewhere near, because Carl kind of glanced over it, that it's not yet kind of in the spec, but is it somewhere near, or is it at least at the top of the list?
So I guess Carl will probably be able to talk more specifically about the intersection PEP, but just to clarify, that's a list of draft PEPs that are actually like in the PEPs repo, like someone has made a pull request, like get that in there.
Yeah, the status of the intersection PEP is that there's a person who has done some work on a draft. There was several years of work trying to hash out what the semantics of intersections should be. The typing core concepts section that I added to the typing spec was in part motivated by clarifying some questions about the meaning of any that came up in those discussions, because we needed that clarified before we could even figure out what intersections mean. So that's progress, and I think we have an agreement now about what the semantics that make sense for intersections are. Personally, I'm not prioritizing work on a PEP because one of the things that we need for a PEP, especially in a very complex area, is a reference implementation so people can play with the semantics. And so I'm focused on providing a reference implementation in TY, and I don't really want to spend time on a PEP until I can point to that and say, I think this represents what we want in the PEP. So.
Yeah, I should say, I think there seems to be forming a general consensus that intersection types are like one of the, because they always like, there's so many new features that could be added to the type system. So there are probably like dozens. Many of them don't have a PEPs. They might have an issue somewhere. Somebody proposes something. It's just completely unrealistic that all of them would be added in the next year or 2 years, or probably even like in 5 years. So there needs to be like pretty strict prioritization. I guess the one thing is, so there's constraint like, okay, we need something that's kind of sufficiently high priority because there's no bandwidth to go through all possible PEPs, and also somebody needs to write the PEP. So I feel like in the intersection types case, it's like the consensus that if I'm reading the room correctly is that it's pretty high priority, but still the work needs to be done, and there's still a bunch of work remaining, but it looks like we are making some pretty good progress. So I'm kind of hopeful that it'll move forward like relatively soon.
On the topic of documentation, I think like one great thing about types is they help make documentation better. And like sometimes it's nice when you can read the name of a function and the types and you're like, oh yes, I know what this does. And to that extent, sometimes I read the very excellent like standard library docs, but I still want to know what the types are. And then I like go to the GitHub for typeshed and I'm like digging through. Would there ever be a point where we might consider just like having a version of the standard library docs that just have types in them?
Well, I think this is probably up to the core devs to decide whether that's something like, whether it's desirable, and also like that's one, there's like general kind of decision, but then also who should decide what the types are they just lifted from typeshed, and like how we need to figure out how to keep them in sync, because it would be like super confusing if the docs say like one type and then typeshed says something and typeshed is still kind of evolving. Even like the standard library types, even some like, I think like dictionary, like dict.get, the type changed relatively recently and kind of like actually impacted. It's quite a big impact. So basically it's kind of a moving target. So it might be a little bit early. Like that's my take, but maybe, but I have no idea.
I mean, this isn't exactly an answer, but one thing we want to prioritize in having a good IDE experience is that you want to be able to like hover over things, and then hopefully you can see the types, and if it's done well, also some form of documentation, and then reduce the need to always be visiting like the website for typing docs.
Yeah, so this is a bit of a more long-term thing, but do you see any real hope towards phasing out and deprecating explicit typefiles? I mean, it's kind of a very bizarre feature of Python's type system. It interacts in unexpected ways with other sorts of global variable support, and no other language I know has it. So like it would be awesome from an implementer's point of view to get rid of it.
I mean, we can't really even have that conversation until Python 3.12 is the oldest supported version of Python. So it's, I mean, it would certainly be a nice wart to get rid of, but we're a long ways away from that being even something we can consider. If you can't hear that, the suggestion was we should really have a tool to auto-convert old type vars to new ones before we consider removing.
Alex, we have that enough.
Yeah, I think there's a wider discussion about like backward compatibility, and I'm not the one to make that decision probably, because this is will impact like a huge number of users. So I'm just bringing up some like concerns with I know some people that own like large Python code bases. They spend a ton of time, and there was a talk at Python Language Summit about this. Just like upgrading to a new Python version is like huge amount of work. Yeah, it's not just your code. You might have like millions of lines of code, but then all the third-party libraries, and some of them are unmaintained, and all sorts of stuff, and C, API, whatnot. So I think there's a delicate balance between like cleaning up old stuff that's kind of obsolete, and then actually making it kind of practical, making Python a kind of pragmatic programming language for like all kinds of projects, even though because there are projects that are like massive, but then they don't have they used to have like, I don't know, 20 full-time people working on it, and now they have like 2 that have to maintain it. And if they're like, hey, you can all of that stuff that's written like 10 years ago, you need to kind of upgrade to this new thing. And really the conversion tools kind of work like 100% without human intervention. So it's kind of, I think it's a really complex issue that's
I mean, I think any deprecation should be like trailing what we observe in the ecosystem, not like trying to force a bunch of people to do a bunch of extra work. So that probably means it'll be a long time.
Well, it's 5:57, so I think that this naturally ended exactly on schedule. And unless there's a last question, I think we can call it. Thank you to the Typing Council.
Thank you to Stephen and Carl for organizing this great summit.